tower enhances thermal comfort. Sloping roofs integrated with solar panels further improve environmental performance and energy efficiency. To arrive at the solution, we developed and tested 3 design iterations through daylight and shadow analysis. We have achieved an FSI of 1.54 and a hybrid ventilation efficiency of 94.7%. As we move to the interiors, our intent is clear: to make it feel like home. Our space opens to a warm, open-plan environment where we use natural materials. We use repurposed furniture and soft zoning elements to keep informal, flexible, human-centric design. We have also used light as a design tool for bringing calm, consistent illumination that enhances comfort and reduces harshness. This is how we achieved what Praveen wanted.
Coming to the engineering and operations, we have multiple construction constraints, and we have chosen isolated footing for cost-effective and efficient foundation system. A waffle slab reduces dead load and embodied carbon while maintaining structural performance. Hirda blocks improves durability over conventional bricks. The terracotta facade and wind tunnel system enhances passive cooling and natural ventilation. Lightweight steel truss and bamboo roofing significantly reduces carbon and weight. The building learns to protect itself. Now, coming to the we are reducing the pollutant mitigation PM10 to 30 to 40% and PM2.5 to 25 to 30% through a process called interception. Coming to the HVAC load, we are using mixed mode ventilation strategy utilizing ERV based ventilation in the basement from MACD World and by energy efficient fans. We have achieved CFM in the interiors through wind tower fans and natural ventilation of 1589.15 CFM. What leaves the building is just as important as what enters it. Coming to the waste management, we are partnering with Swachh that transform Mueller-level pollutants into durable SPV blocks, where we are surpassing the 90% IGBC net zero waste requirement for our 75 occupants. Coming to our app, Karigar Sync, that documents community participation from the very start. Local residents are invited to join plastic collection drives and textile donation, and it has a 14-piece dashboard with all the community and construction data. Now, for the collaborative innovation, this is our team with all the team contests. Going to our innovative how can a facade turn Pune's hot air into a cooling system? Introducing our Varha, the evaporative facade. Varha utilizes the Venturi effect to draw in natural air, passing it through a built-in horizontal cyclone filter, where centrifugal force flings dust against the tube wall towards an end collection point. Simultaneously, water seeps through the clay body to evaporatively cool the filter airstream, creating a clean, constant thermal barrier for the building. Consulted with coolant. Coming to our next innovation, that is our silica plastic blocks, where it is manufactured with a ratio of 50:50 of shredded plastic with building debris that we are producing on site by leasing a portable machine from Rhino Machine. Coming to our Bint Khurchi. This is a wooden frame and a writable vinyl surface that serve as a functional interactive wall where it can be transformed into a seat whenever required. Coming to the Hirda jaggery blocks, we are using fly ash as a binder, hydrated lime as for the overall block stability, and kadukai and jaggery for the natural bioadditives. Coming to the baggies panel, as Pune generates 5 million tons of baggies waste, we generate the leftover sugarcane fiber transformed through a thermocompression process to make the baggies panel. And for the recycled fabric waste, we are partnering up with Mimansa that transforms the textile into our interior panels for our office, and it is also employing self-made groups women in Pune.
बीज यहाँ पे हर वॉट मायने रखता है और हर व्यक्ति भी. Can innovation make buildings not just smarter but healthier? And how do we measure the success of an innovation? By its novelty or by its impact on its occupants? For this, for health and well-being, we have 3 key pillars, which is physical well-being, mental and emotional well-being, and environmental well-being. The goal that we have achieved is indoor temperatures that is consistently maintained at 22 to 30 degrees Celsius, which is in compliance with the IMAC model, and air quality ensured at 1589.15 CFM. This we have achieved through passive and active strategies. For thermal comfort, we shaded the east and west facades, introduced a cyclo-evaporative facade, used stack and cross ventilation and also hybrid ventilation strategies, which brought down our cooling load by about 83%. Then we had an average operative temperature of about 24.6 degrees Celsius, and we also met about 94% of the annual comfort hours. For indoor air quality, we had ERV system with humidifier in the basement and indoor biophilic plants. For daylighting, we had double evaporative facade and a balanced daylight distribution. And for facade radiation, we tackled it through shading devices. For biophilic design, we had integrated natural materials, indoor biophilic plants, planter boxes. For mental and social well-being, we had social nodes and collaborative zones. For inclusivity and exclusivity, we had ramps, lifts, tactile paving. Talking about the well building standard, which we had used to quantify this data, across all of these different categories, as you can see, these are the different points that we have scored, and we could achieve a platinum certification in precondition as well as an optimization. So now, how much energy does comfort actually really need? These are the questions that we are going to tackle here. From this, the energy goals that we had achieved was, the EPI achieved was at 40.05 kilowatt hour per square meters per year with an EPI reduction of about 83%. We had also generated energy of about 71,000 watts. And we could achieve gold certification in IGBC green new buildings and super ECBC standards. So what impacts did they create and how did we achieve these? What were the strategies? The base case had an EPI of about 233.66 kilowatt hours. Using materials as listed there, lighting and smart systems with evaporative cooling and wind towers and equipment controls, the cumulative of all of these led us to bringing our EPI down to 40.05 kilowatt hour per square meters. So how much energy does a building truly need? We calculated the annual cooling demand from design builder and equipment load of the building. And from this, we could gather that we needed about 71,000 watts of electricity. And for this, how much energy are we able to generate here? From all of this data, we could gather that if we use 66 solar panels, bifacial solar gain panels, we could generate a surplus energy as well in the months from January to April and November, December as well. So the next story is, how is this energy being preserved? This energy is being preserved in our 4-hour battery backup of lithium iron phosphate energy efficiency 90% solar storage system, which is mainly contributing to lighting, ventilation and emergency systems. So the overall energy consumption overview shows that the cooling and electricity is the most dominant energy use, where solar gains tend to become a major contributor. Ventilation and infiltration rates change throughout the year, but they become more during the warmer months of the year. So, and this data was quantified using the IGBC Green New Buildings version 4. We have shown the points that we have received here, and overall we could achieve 78 points, which falls under the gold certification here. Now talking about water. Pune faces a water crisis. We all know that. We all have seen the news. This is because of rapid urbanization, the groundwater depleting reserves and seasonal monsoons. Now India is facing a water crisis and we are designing buildings which will respond to it. Talking about that, the energy goals that we have achieved here is that we have achieved a 59% reduction and 100% of our wastewater is being recycled. Some amount is also going into the ground, which makes us net water positive. From this, the total consumption, which was in the base case, we have brought it down nearly half in our project, which is Beach. And we have also reduced our consumption for workstations as well as for exhibition spaces. And this is done through different fixtures and through different strategies which have been listed here. Talking about the rainwater that is being harvested, we are harvesting nearly about 550,000 liters of water. And this is being filtered with a 90% efficiency rice husk activated filter. And with this, the groundwater is also being recharged through an Ola, which is a buried porous terracotta vessel, which has more efficiency when compared to a conventional surface watering system. And this basically shows the rainwater that is being used for all different purposes and how much of it is going into groundwater and how much of it is being recycled. So from all of this data, we can know that we can go into year-round resilience. Talking about wastewater, we have known that by all the strategies that I've shown above, we could aim at 59% reduction. ACOM, our industry partner, talks about Nutrisorb, which is a wastewater management solution. It combines both grey water as well as black water, and it dilutes the highly concentrated amounts of BOD and COD, which reduces our overall organic load. And this wastewater is then used in the facade systems with a misting system, and it has been it is connected to a thermal sensor, which mainly provides the water during the occupational hours for 8 a.m. to 6 p.m. And these are some of the calculations for the same.
Throughout the project, every decision was evaluated by three guiding lenses: what can be optimized, what can be eliminated, and what can create a long-term value. I'll begin with embodied carbon. Before a building is occupied, a significant portion of its lifetime emissions has already been released through material extraction, construction, and manufacturing. To address this, we prioritize low carbon materials, carbon negative materials, local sourcing strategies. These measures basically have achieved a 75% reduction in embodied carbon and transportation related emissions compared to the baseline. Key materials that reduced embodied carbon included a cross-laminated bamboo waffle slab, an optimized HVFA structural system, an on-site Hydra block production using excavated soil, and materials such as lime plaster and terracotta. Land sequestration was also assessed separately. Local procurement and on-site manufacturing further reduced the transport emissions to just 0.2 kg CO2e. To verify these outcomes, a detailed one-click LCA assessment was conducted with guidance from our industry partner 1.5 and using SDI's functional unit framework. The result is a building that not only minimizes the upfront carbon impacts, but also demonstrates how material choices can actively contribute to a lower carbon future. When we talk about resilience, resilience was driven by anticipating future risks, including heat stress, flooding, water scarcity, power outages, earthquakes, and fire hazards. Through passive cooling, flood mitigation, net water positive systems, 100% solar backup, seismic design, and comprehensive fire safety strategies, we created an office that remains safe, resource efficient, and operational under changing future conditions. When we look into affordability, as a result, the project has achieved a 24% reduction in the capex and a 75% reduction in the opex. Now, you might assume how we've achieved these. So we've basically reduced the capital footprint by local resource utilization, on-site material production, quantity optimization, and equipment reduction. The other method that we were using was with a 1.21 year payback period and a 15% reduction in costing through government subsidies. The solar PV system delivers strong returns, while rental offices, the exhibition spaces, the workshops, and the CSR partnerships create a sustained revenue system. When we talk about the operational perspective, we have passive cooling, renewable energy, water self-sufficiency, and prefabricated systems. These result in an annual savings of approx 5.56 lakhs. The construction efficiency was seen through parallel construction, with prefab activities going simultaneously with the site activities, and the project can be completed in 12 to 14 months with 15 to 20% efficiency as compared to an RCC construction. By balancing sustainable investments with efficient construction, we've lowered the overall cost while delivering greater life cycle value.
But these are not just percentages. They are lower bills for businesses, healthier workplaces for employees, opportunities for local artisans, income for communities, knowledge for future generations, and a hope for a future that desperately needs it. What started as Praveen's dream became our challenge, and somewhere along the way, it became much bigger than a competition entry. It became a question: if we know how to build better, then what excuse do we have not to? Because a new India does not need another building. It needs buildings that give back more than they can take. There were 13 of us on Team Avya. We planted a tree each in the Vetalya site, 13 trees, a moment we were proud of. But then we did the math. After everything we've done, after every drawing, every calculation, every strategy, we're still 13 trees away from neutralizing our own carbon footprint. And that's when it hit us. We are Team Avya. 13 students, one vision, one prototype, one belief. The buildings we decide today will decide the Bharat we inherit tomorrow. Because we are the makers of the new Bharat. And our project Beach began with a simple belief that even the smallest seed of design can grow into systems of real change. This was our contribution as the makers of the new Bharat. Now the choice is up to you. Dhanyavad.
Thank you, team. You finished well in time. Let's hear the jury comments and take questions from them. Vaishali, I'll start with you.
Hello? Is it working? So very well presented presentation, I must say. It was very nicely coordinated and everything was put up on time. So that's great work. So I wanted to ask a question about the waste management. So you have been talking about waste that you have managed waste, but what about the post occupancy? Like when the waste is generated on site, what are you planning to do with that?
So what we have done with waste management is we've partnered up with Swatch. So we've explained the pre-construction process, but for post-construction, we have had a system with Swatch where they distribute the waste in a way that everything gets repurposed and it does not end up in a landfill.
That's okay, you can speak.
Um, yeah. So on the basis of
So are you looking at generating energy out of that waste later?
um, yes, as you can see in this, we segregated the waste into office waste as well as the workshop waste. So the workshop waste will produce significantly less waste than what the office produces. And in that diagram, we've shown like where the waste goes. It is segregated according to wet waste and then dry waste. But we cannot do it on site because it's a very limited site. So
Okay. Another question is regarding the overall energy consumption. So you said that you are reducing on 83% on your energy reductions. So how are you considering that in terms of the base case when you had a very limited conditioned area? So are you considering the similar conditioned area in both the cases, or you are considering a higher conditioned area in the base case? Because this is a good amount of energy reduction, and I think I've also commented this in the uh, review, right?
So our base case, which we considered, had similar area, which was a normal shoebox rectangular model, but we had iterated it with the three different forms we had shown, and out of which the one form that we have gone with is the case. But in that, which we had you had also mentioned in the comments, that we only have HVAC, a split AC in the basement. That is only being accounted for nearly about 13 square meters, and that is what was taking up some amount of the energy. So that's why a major chunk of the energy gets reduced, around 83%, because that's through the passive and active strategies that we have used.
Okay. Thank you.
Yeah, I think overall a good, well put together presentation. just had a couple of questions and maybe you could answer those. I would have liked to see a little bit more detail on how you were trying to manage the PM 2.5 and PM 10 processes. I do understand that you have a proprietary technology where you're using the clay turbinator, but a little bit more explanation on that would have been helpful. And there's a lot of talk about humidifying the air. And what the number showed was you were trying to do that almost through the year. But if you look at Plune's climate, there is quite a bit of time in the year where the humidity levels outside are very high. So if it's a very hot and dry climate, I would have totally bought into this concept. While many months of the year might be conducive for that type of technology or a concept, I don't see it unless you show me more numbers and more evaluations of how adding humidity when already the outside humidity levels are pretty high are going to help create that thermal comfort, right? Maybe you can explain that. And then also you talked about the solar chimney or the stack thing you're creating, and it's located to one side of the building. So cross ventilation, how is the airflow happening? A little bit more detail on that would have been helpful. One last question, or probably two, is one, you talked about two kinds of bricks. One's the plastic waste generated one, and the other one's the Hirda. Where it is used and what's the percentage? Is there a combination of where they're being used? And the last question is, like you said, only 4 hours of backup on your from the solar, right? For if you're looking at resiliency in a building, do you think 4 hours is enough? Right? I know a lot of questions, but if you forget something, I can.
So, sir, I would like to question the humidity one. So, basically, there's in our BMS system, that is the Karigar sink, we have a thermal sensor there. So, basically, it senses the humidity that is outside and inside the building, and it generate like it. The water then only seeps that much amount of water that is required, that does not increase the humidity level inside the building.
But you also have a ERV system, right? ERV plus humidity, like
ERV
humidifying
is
it
only in
by.
the basement. That's where the cyclo-evaporative facade is not there. So it's only to purify the air within the basement.
Okay, that makes it more clear. Okay.
And can you just repeat the last question that you had asked?
Yeah.
About the battery backup.
Yeah.
We needed a 4-hour energy battery backup. It's mainly for lighting, ventilation, and emergency systems. It is mainly to power that, not for equipments or anything else. This is under the NBC norms, so that is what we had gone with.
So basically, if you're looking at resiliency, you need to look at more number of hours or days of resiliency of being able to operate the building in terms of an outage, right? If you have good amount of generation on site, why not utilize it, right? And I think the bricks part you can look at it, and the roof. Particular reason why you oriented it west, not the most optimum orientation to put your solar panels on, right? You had a south facade. I mean, you could have sloped it south. I know it's an architectural design decision, but I question that as to why you did it that way.
We have tried to battle it with the materials that we are using. So our form that we have used on the roof, we have tried to mitigate it with the materials which are bamboo based. So it helps us with the solar panels as well. We are mounting the solar panels also at a height with the ground clearance, and they are bifacial gains, so that it would help.
When you say bifacial, right, it's only certain conditions where the bifacial solar panels work.
Yeah.
We can get into it a little bit more detail, but I felt like you were quite close for the last tie of the class, like certain tie of the.
Thank you.
The overall presentation is good. It is well thought through. I feel, as Sandeep actually was suggesting, that at the last thing actually about this energy evaluation and then the selection of the system. A small example, like a base case, is considered 266 kilowatt hour per meter square per year. So the base case itself actually is very high, and then I want to check actually what is the um, either it has to be like a even in if you air condition 100%, you will not get the base case of 266. So
I think because of the floor area that we were taking, since this one, the model that we have right now, does not have that much depth. But when we take a rectangular shoebox model, there's a depth as well. So that must have led it to 233.66 kilowatt hour per square meters.
I think that's where practically when we do a simulation and then check, that's where it is. And also on the solar, as Sandeep actually was suggesting, like if you consider bifacial solar, so the bottom roof also there should be a space, and the bottom roof also has to reflect the light. Then only it can produce the solar, the PV. So these two are my
For that, since we did not have the reflectivity on the roof,
yeah.
we thought that we could mount it at a height. So we would have more clearance that way.
Sure.
So you were asking about where which brick goes, right? So to just sum it up, the SPB pavers that we're using are going on the pavement. Then we're also using the SPB blocks only in the bathrooms because they generate a lot of carbon emissions. Whereas the rest of the building is the external facade is the Hydra block.
Thank you.
Thank you, jury members. Thank you, Team Avya. Let's take 5 minutes and get ready for the next presentation. Our second presentation is from Team Greenline HQ. They have worked on the PCMC fire station headquarters located in Pimpri, Pune. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I will stop you and ask you to end your presentation. After that, we will have 10 minutes for the Q&A session. Please keep your answers direct and to the point. Okay, team, all the best.
Thank you. Good morning, everyone. As cities continues to grow rapidly, emergency infrastructure becomes increasingly important. These facilities operate 24/7 per day and plays a critical role in ensuring public safety. At the same time, they consume significant resources and must remain operational under all conditions. This led us to ask a question: can a fire headquarters be sustainable while still meeting the demanding requirements of emergency responses? To answer this, we represent Agnistha. Agnistha is the outcome of the collective efforts of 15 students from Team Greenline Headquarters, guided by our academic mentors and industry partners. Before starting the design, we wanted to understand the users of the building. So we visited multiple fire stations in and around Pune and interacted directly with firefighters and officers. Through these visits, we understood not only the functional requirements but also the day-to-day realities of firefighters. We learned about the importance of quick response times, efficient movement within the buildings, visual connectivity between the teams, access to daylight and fresh air, and spaces that support physical and mental well-being. These learnings became the foundation of our design. Moving on to the site. The project is located on 25,371 square meter 371 square meter of area in Pimpri Chinchwad. One of the major opportunities was the existing 3 lakh capacity water tank located on the site itself. At the same time, the site presented challenges. The eastern edge is surrounded by residential development within approximately 45 meters, and the site access is relatively narrow for emergency operations. These conditions informed our planning decisions from the beginning. The next step was understanding the climate. The most critical period occurs during the summer months, when temperature reach up to 38 degrees Celsius and humidity drops from 30 to 40%, which creates thermal discomfort. Wind analysis showed prevailing winds from the west during summers and monsoons, while winter experiences winds from east direction. Based on this analysis, we established 3 key design goals. First, achieving 100% adaptive comfort. Second, maximizing natural ventilation. And third, maximizing daylight availability across the building. Every design decision was evaluated against 3 goals, starting with the form development. We first separated building into 2 zones, one public spaces and 24-hour emergency operational spaces. The public block was then tilted to reduce direct western heat gain while maximizing prevailing wind from the west side. Courtyards were introduced to improve daylight penetration into the buildings. These courtyards were further optimized into double courtyard configuration, creating mutual shading, enhancing cross ventilation, and improving overall thermal comfort. This resulted in the final form that responds directly to the climate and function. Moving on to the zoning. Since one of our objectives was to minimize refrigeration-based cooling, only critical spaces were considered for conditioning. The zoning was developed based on fire department adjacencies, operational requirements, ventilation needs, and occupancy schedules. This allowed us to reduce conditioning areas while maintaining functionality. The narrow side entry also required careful circulation planning. To address this, we separated the entries for 2 bays, one for users, public users, and second one is for emergency operations. Moving to the basement plan. Basement accommodates parking and service infrastructure while ensuring universal accessibility throughout the project. At the ground floor, we have operational heart of the headquarters. The apparatus bay accommodates 18 vehicles while 4 ready to go parked and positioned outside the building. The floor also houses workshop and maintenance facilities along with supporting operational spaces. A mezzanine level above provides storage for 5 additional fire-specific equipment systems directly above the apparatus bay. So, directly above the apparatus bay, there is an accommodation system provided for firefighters for emergencies deployment. The public functions, including the museum, auditorium, and dining spaces, are located on the opposite side. The second floor houses office spaces, while the uppermost level accommodates training facilities. By understanding the movement pattern of different users, we organize the building vertically to reduce lift uses and improve operational efficiency. Moving to the roof, the terrace houses a 286 kilowatt PV system generating approximately 116% of building's annual energy demand. Moving on to
So the most important our innovation addresses the apparatus bay. So this is a roof lantern, which is a combination of daylight ventilation. So in the apparatus bay, there are 18 vehicles at present. So whenever the pollutant levels increase, the louvers operate progressively. So as you can see on the side, so there is a fan on the top which continuously operates at normal conditions. So when the pollutant levels increase, the louvers open progressively, and the vertical glazing brings in daylight. So these are kept at separate intervals to get, because apparatus bays are huge spaces that are like in our case it is 30 by 36 meters. There is also a filtration system that is provided inside the, so where we can see in this block we have a filtration system. Right now it is not shown. So and additionally, so when these are placed on the roof, we will have plants that make the system more robust, because the traditional tailpipe extraction systems are costly, and we wanted to look for an alternative solution in our case. Coming to the energy performance. So doing the energy analysis, we checked our baseline model against ASHRAE 90.1 2022, which is the latest at present. So the first most cost effective is the shading devices. So we have 0.6 meter overhangs and 0.5 side fins, which are based on our annual shading requirements. Because the roof receives maximum radiation, we have a 75 concrete PUF insulation with brickbat waterproofing. Porotherm blocks replace conventional bricks. We have used single glazing all throughout the building, and we have installed fins, eco-dry films on that to reduce the embodied energy, because DGUs have a lot of that. For lighting, we have reduced the LPD to 40% from our baseline. For cooling, we wanted to go with a low refrigerant system. So we have introduced an indirect direct evaporative cooling system, which is very ideal for the Pune climate. There are lighting sensors and occupancy sensors installed to reduce the energy consumption, as the building is designed to harness maximum daylight. So our total annual energy consumption comes to 3,87,778 kilowatt hours, and our annual renewable energy generation is 4,50,238 kilowatt hours. So this makes it a net positive building. Our net EPI becomes a negative 6.5 kilowatt hour meter square per year. Talking about health and well-being. So low energy buildings do not imply low comfort buildings. We did a UDI analysis in which we, because of the thin floor plates, this gives us an advantage so that 90% of our annual hours are visual comfort. We For the air quality monitors, we have in the apparatus base, office, and main lobbies. So the tracked metrics are CO, NO2, PM 2.5, and TVOCs. So talking about the outdoor comfort, so we are using 100% natural fresh air system, which is the IDEC. This is very ideal for the Pune climate. Uh, so this is a graph where we have overlapped the dry bulb temperature and the relative humidity. For the summer months, we are completely operating it on IDEC system because it works best when we have higher temperatures and lower humidity. For the monsoons, there is a DAMA technology that is used, which allows the system to work only on indirect cooling. So we are going for natural ventilation and IDC system. The because the cooling is not so efficient in monsoons, but however we already have the dry bulb temperatures outside that are within our comfort range. So the IDC system will help us to reduce the humidity levels. For the winter months, natural ventilation is sufficient because the outdoor dry bulb temperature are well within the IMAC range. So we can say that we achieve 100% adaptive comfort within 90% acceptable range of the IMAC. So detailing about the IDC system, we have two AHUs providing. So one is the operation for the 24/7 spaces, and the second one operates for the 10 to 6 a.m. 6 p.m. spaces. We have used efficient fans for the same. For a VRF system, we have a very small capacity of serving only the critical spaces, which is a 12 TR system. And natural ventilation occurs for most of our circulation spaces.
Next, moving on to the water performance of the building. We are 70% water independent with 100% wastewater treated on site, 100% flushing using recycled water, and 100% rainwater recharge. For domestic usage, we have reduced the water usage by 37% using water efficient fixtures. Making use of native and adaptive landscape, we have reduced the water demand from baseline of 6 liters per meter square to 1.7 per meter square. The water demands for vehicle washing of fire tenders and PPE kits washing are also accounted for. The makeup water for IDEX system is considered as 1.25 KLD. We have installed bio STPs on our site to facilitate the filtration processes and making reuse of the water. We have installed water meters on the major consumption and supply system. We have provided for 55 KLD of potable water tank, 20 KLD of recycled water tank, and 100 KLD of underground fire water tank with 10 KLD of terrace fire water tank. Now coming to the embodied carbon, we have reduced the carbon footprint of our building through material optimization. We have achieved the emission reduction of 52%. The main key drivers and materials alternatives that we are used for the structure, we have used 50% of GGBS along with Portland slag cement and 60% of recycled steel instead of traditional RCC construction. For walls system, we have used porotherm blocks instead of the standard red bricks. And for tiles, we have used Kota tiles instead of the ceramic tiles. We have also noticed that the material production emissions are more than the transportation emissions. And through our material optimization and reduction in operational energy, we have also achieved 65% reduction in operational carbon.
Coming to the resilience, a fire headquarters must survive the disaster it responds to. So, for flood resilience, we have managed to design a peak runoff capacity of drainage, which is 1,235 cubic meters, and we have a site area of 25,000 square meters. And for water security, We have water autonomy of 6.8 days. So for energy resilience, we have DG backup of 125 kVA, where we have paired the battery storage and the grids and the solar panels with 100 kilowatt hour. Coming to the access and recovery, we have designed a high plinth, elevated plinth. So coming to the value proposition, all of this innovation is is financially feasible, as our projected cost is 43.43 crore by using the GGBS in concrete, IDEC based cooling systems and water efficient strategies. Uh, by coming to the value proposition, energy performance, we are providing a net zero positive building and 70% water independence. Embodied carbon, for we have reduced the carbon emission by 52%. LCA performance is 65% reduction in operational carbon, and we have achieved 100% thermal adaptive thermal comfort. Value for the visitors and firefighters are thermal comfort and indoor environmental quality, advanced training infrastructure, on-site wellness facilities, and operational readiness. So, by concluding, ultimately, our vision states designed to protect those who protect us. Agnistar stands as a benchmark for future-ready net zero emergency infrastructure. Thank you.
Thank you, team. You did a great job. Let's hear the jury comments and take questions from them.
Yeah, hi. I think overall a pretty good presentation. Could have been a little bit more storytelling or otherwise, but I think overall good. There were a couple of things where I felt like you should have looked at it, or maybe I have questions about it, which I'll ask you about. One was the Eco Drive films that you talked about. I understand that you spoke about the double pane windows having higher embodied carbon. But when I looked at the numbers, it seemed like the numbers you're quoting were very low, so it might not have included the fenestration or the full component of the glazing. And in general, films are only used in cases where it's an existing building where its retrofitting is a problem. So I would still suggest you to go back and look at what the U values and SHGC and visual transmitted numbers are, compare it with what you would achieve with a double pane window, and do that overall comparison. The second part was I still see that irrigation takes quite a bit of water consumption. I know you mentioned that you're using native species and all that, but driving down water consumption that you're doing on irrigation could be something that you kind of look at. Form base, I really like the way you've articulated the form and the orientation and all that, but with the shading elements, I think a little bit more diagrammatic explanation as to how you came about with those dimensions, those 6 meters and 600 mm, and for the horizontal and the vertical dimensions would have been good. So with the HVAC system, there's always been a talk about IDEC, but no other evaluations were seen in that. Did you evaluate other systems, and why you chose the IDEC? I know it's a good system, but just those numbers were not very clearly seen. Last question, energy storage. You said you have a battery pack in the numbers, but how many days of
For 2
isolation?
days.
Sorry?
2 days.
2 days. Okay.
So I'll answer each question one by one.
Yeah.
Talking about the EcoDrive films first. So we actually spoke with the manufacturer and the one who supplies. So the vendor is in Delhi, and we actually obtained their brochures, and they also send us the embodied calculation. So that is why we went for these. And when you compare with the numbers like the SHGC numbers and the U value numbers with the existing DGUs, the films perform really better than the DGUs. And also because we are already providing shading for our windows, we did not want to go for DGUs. So because we even in our skylights, like as you can see, we have vertical glazing, so there is no horizontal glazing in our building. Like coming to your second question, so can you please
The irrigation part. Yeah.
yes, sir. So like when we were working on that, so all the species that we have provided are native species, and the exact number, so 1.7 was like given to us, and the IGBC states that it is 6 liters when you're going for conventional. So we had considered that kind of reduction in our building.
Yeah, I think the last question probably you could address is the evaluation of HVAC systems, IDEC versus the
Yes,
other
sir.
ones.
So I would like to mention that we have done a whole lot of simulations. We have multiple files for Design Builder. We actually reached out to around 6 to 7 consultants and people who actually could do that, because in our D3 also we had mentioned how we came to the IDEC system. So then we started optimizing it because nobody could actually figure out how it would work in Design Builder. So we did not have numbers to put there. But instead of that, we found out manufacturer brochures that tell us how the supplier temperatures are. So the basic concept was to like when the humidity goes low, when the delta T is more, you get a better cooling. And in the monsoons, when you have lower cooling efficiency, we can actually use it for humidity removal.
Okay. So, very well presented. I just felt the pace could have been a little more in the sense that you could have spoken more about the project and what was your process altogether to bring it down to this kind of a project submission. Yeah, so I really liked that you have achieved a 90% UDI in your building. So I highly appreciate the form and the overall floor plate optimization. I just felt that there was a little lag in the passive design thinking and the performance-based environmental goals. Like you could have used a lot of passive technology rather than only getting dependent on the HVAC technology of IDEC. So that is one thing I thought that I should mention, because if you would have considered a lot of passive technology, that would have been little more better in terms of your overall energy reductions. And I have a question which was also asked about the films. So I think you have already answered half bit of it. So I wanted to understand, do you have a value for U value reduction with the films?
Whatever the manufacturer brochure has stated, we have considered that in our. So I know they are really low. So it's like
Yeah.
0.5 to 1.
So as per my understanding of the industry, there is very minute U value reduction with the films. So if you are considering it to reduce the overall U value of the material, then that won't work. But if you are just considering the SHGC, then it will work well. So yeah, that is one point. And yeah, for the life cycle assessment, I think you could have done a little more in terms of detailing it. But overall, the submission was really well. Thank you.
Hi. I really like, you said about IDEX system that is used in summer. As an engineer, actually, that is a right system to use. And And then is that a solar chimney? The one that you done a modulation?
Yes, so actually there are sensors that are placed in the apparatus bay.
Okay.
And so when the pollutant levels rise, there is a low energy fan that is continuously working to keep the air changes at normal. So when there are more vehicles that are coming with the pollutants like CO2 and NO2, so we have filters so there are different filters for different pollutants. So we have made a stack of that and we will place it. So right now it's not there because this was actually a sensor based model taking up the smoke and then the lures will operate. But we were not allowed to light anything right now.
But will this be installed at the terrace or where exactly it is?
So this is at the podium level in this section.
Oh.
So this is the first floor level. So this is the day room, which are the fire spaces, and these are the places where it will be installed. So exactly above the spaces which require removal of filtration, like the pollutants.
No, I like you went on trying these kind of things, and I really like the architects doing this as engineers.
Thank you, sir.
And I could see the lot of numbers that is well presented. What I felt was I think in terms of the industry partners, you could have worked with them actually with real MEP engineers and sustainability people are the the vendors close the manner you would have performed better. And other thing is that like you did the study about this, you went and visited
Yes.
many fireplaces, right? Fire stations. There was no mention of the pain points. What is the problem they are facing, and then how are we addressing actually in our design?
So the pain points of them were mostly they don't have like proper spaces for resting when they are. So when one of the officer we spoke to, he came back from a long thing. So it's not only just fire, but fire department handles all the other thing like rescuing animals and other activities as well. So there are some dangers associated with that as well. So there was no proper resting space, no thermal comfort, because one we visited, it was you could call it like a headquarter because this is on a huge scale comparing because the others are small fire stations. Thermal comfort is a very big issue over there. They don't have good resting spaces, and also if they want to sit and work. So when we went, most of the fire people, they were just like walking around. They didn't have a dedicated space. And also now that there are many women fighters joining in, so we have considered that as well, and we have separated out the spaces for female and male as well.
Thank you.
Thank you, Team Greenline. Thank you, jury members. We will be taking a small 15-minute tea break before we begin with the third team. Tea will be served right outside the hall. Folks online, I request you to stay tuned and be with us to support the upcoming teams. Thank you.
is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and the world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through, through. The world is so hot, hot, hot. We're making it
Office Building Division. Our third presentation is from Team Samaved 2.0. They have worked on a project called Upstack located in Baner, Pune. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I will stop you and ask you to end the presentation. After that, we will have 10 minutes for a Q&A session. Please keep your answers direct and to the point. All right, team, the stage is yours.
Good morning, everyone. We are Team Samaved 2.0 from SMEF Big School of Architecture, Pune. And today we present Upstack, a voxel optimized net positive MSME co-working hub in Baner, Pune.
India has over 63 million MSMEs, but here's the problem. They face what we call the ambience gap. In Pune, Grade A office leases runs at rupees 80 to 120 per square feet, and OPEX alone eats 20 to 30% of that. Small businesses simply can't afford it.
So how does Upstack fix that gap?
Through smart passive design, we reduce that OPEX burden by 88%. This saving is directly passed to the tenants, making premium dignified workspaces financially accessible without touching the developer's margin.
And we didn't build this project in isolation. Our project partner, Amar Builders, gave us a site in Baner and grounded our net zero approach with real developer expectations.
The plot is 4,589 square meter. Under UDCPR, the maximum FSI is 3, giving us a total permissible built-up area of 24,049 square meter across 20 floors. We achieved 72% usable area with a 4.2 meter floor-to-floor height.
Now let's talk about the form. Conventionally, architects design massing, run solar and wind analysis, and then reactively fix the flaws. Ashutosh, did we do that?
No, we used a proactive approach. Upstack's form isn't just designed, it's computed. We used multi-objective optimization in Grasshopper. We have designed an algorithm which grows voxels within the maximum buildable volume, constraints by setbacks, ground coverage, and co-placements. Then we scored each voxel to critical sun positions. If a voxel hits 4 out of 10 sun rays, then the value of that voxel will be 0.4. If 2 rays hit, the value will be 0.2. The solver's goal is to minimize that number while optimizing the built-up area. Now I would request Sai to please give the Grasshopper script and the Python script to the esteemed jury for the reference.
So Ashutosh, it's the digital survival of the fittest?
Exactly. It ran millions of iterations and generated a Pareto front, which is a cloud of non-dominated solutions representing absolute trade-offs between built-up area and the shading performance. Then we ran CFD analysis on the best solutions to validate that wind naturally channels for the cross ventilation.
But a raw voxel shape like this is impossible to build. When you simplified that into floor plates, didn't you lose the performance?
Exactly the right question, and we tested it rigorously. So after the simplification, we got 14% reduction in mutual shading performance, and the good part is we got 32.3% reduction in EPI just by the form alone after the simplification of the form.
Okay, that checks out. But how does it actually feel like for an MSME employee?
So the performance data sets the stage for human experience. The zoning of the building features a ground floor retail activating the urban edge. Above that, the mix of large, medium and small MSME spaces and pay-per-use units. For the fire safety, we are fully NBC compliant, featuring a fire tower pressurized staircase and a fire lift. We have dedicated refuge areas on the dedicated floors. For the facade maintenance, TiO2 coated terracotta panels are largely self-cleaning with rainwater because they break down the organic substances. So even the bird littering isn't the problem. In the dry season, the panels rotate on the metal rod for the direct manual cleaning and the maintenance.
Now let's talk about the engineering and operations of Upstack. Supporting an 85-meter tall tower with shifting volumes is a serious structural challenge. For that, the team has implemented a hybrid core outrigger system with encased composite columns. When we tested it through structural deflection analysis, our simulations confirm exceptional rigidity. IS 1893 standard recommends 170 mm deflection for our 85-meter tall tower. Our deflection was just 8 mm, keeping our sway under 5% of the permissible limit, giving us a highly stable structure. The structure also helps us to eliminate the redundant material, hence reducing the embodied carbon. If it is the structure that keeps the building standing, it's the BIMS system which makes it breathe. It continuously monitors indoor and outdoor climates, and when it's favorable outside, it alerts the users to open the windows. And if it's not, it shifts to the mechanical cooling mode. This precision has allowed us to right size our HVAC system from a baseline of 627 TR to just 332 TR.
Let's talk about collaborative innovation. Every technology in Abstract was introduced through collaboration, validated through a partnership, and refined through a multidisciplinary dialogue. Let me show you how. The outer skin of our double skin facade uses TiO2 coated terracotta panels. We consulted directly with Toto, who manufactures these coatings, on real world effectiveness and practical integration before finalizing the specifications. For thermal mass, we embedded the phase change material in our office furniture and server room panels. So every workstation becomes a thermal battery, absorbing heat during the daytime as it melts, releasing it at night as it resets. We consulted with VKE Environmental for placement strategy, collaborated with Daikin to validate the aluminum casing for heat transfer efficiency, and confirmed local procurement of RT28 PCM from Plus Advanced Technologies. For acoustic and thermal insulation, we have 100% biodegradable mycelium panels sourced from Grow and Bio, which are lightweight, fire resistant, and commercially available today. Our energy generation relies on two systems: peroxide silicon tandem panels, a proven technology demonstrated by Hanwha Group. We have aligned with India-based P3C technology for procurement as they advance in R&D, and our Kirigami CIGS modules, which are validated through GCR analysis that we will detail in energy section. Every innovation here has a named partner, a procurement path, and a constructability answer.
Now we move on to our health and well-being strategies. Let's address daylighting first. Without the DSF, illumination was highly uneven. 700 lux at the perimeter, dropping to 98 lux at the core. With DSF integrated, our SDI is exactly 50% and annual sunlight exposure is kept below the 10% glare threshold. Perimeter workstations use natural daylight. The shaded core uses automated high-efficiency LEDs to compensate for the dense shading on the south, east, and west. We increase the VLT of north glazing to maximize soft diffuse daylight.
Our CFD analysis confirms that the building massing naturally funnels the wind to ensure deep cross ventilation across our floor plates. To further protect our indoor air quality, our facade features a photocatalytic TiO2 panel matrix that breaks down up to 40 to 50% of airborne pollutants like NOx and VOCs under sunlight. When the outdoor conditions aren't favorable or if there is an overcast sky, our BIMS failsafe activates and alerts the users to close windows and switch to complete HVAC mode, keeping our CO2 strictly below 800 ppm all year round.
For the thermal comfort, we use adaptive comfort model alongside the CFD. Our annual mean operative temperature is 24 degrees Celsius. On a specific day in February, the operative temperature goes up to 26 degrees Celsius. PMV value is plus 0.36 and a PPD value is 7.76%, which is well below the 10% discomfort threshold. Abstracts achieves 1050 hours of full natural ventilation with fan assist, bypassing the chiller plant entirely for that duration.
Let's talk about energy performance. Our optimized geometry did the heavy lifting, dropping baseline EPI from 181 to 122.94 through form alone. From there, the mixed mode ventilation plus HVAC system drives cooling EPI to 54.32. Advanced lighting optimizations save over 292,000 kWh annually. Final building EPI 55.62 kWh per meter square per year, with a total annual consumption of approximately 925 MWh. To meet and exceed that demand, two generation systems were used. First, Kirigami CIGS thin film on the roof and security canopy covering approximately 1500 square meter, but the 3D folds give us 1600 square meter. These folds act as passive solar trackers without any moving parts, able to generate 675 MWh annually, generating 148% higher output than a standard monocrystalline system on the same footprint. Second, 1300 square meter of perovskite silicon tandem panels on the south facade and co-cladding, generating 468 MWh per year due to their double absorption properties, which makes them 36% more efficient than the standard BIPV panels. Finally, Abstract generates a 25% annual energy surplus.
Let's come to water performance. Our water strategy focuses on achieving a net zero closed loop water system, reducing demand, collecting available resources, treating wastewater, and reusing it within the campus. Demand reduction as per NBC. The base demand of 45 LPD is reduced to 22 LPD using low flow fixtures from Kolar, Sera, and Jaguar, achieving over 50% saving. Collection. Pune averages 720 mm of annual rainfall. Roof and terraces harvest that runoff into a dedicated rainwater storage system. Annual collection meets annual demand. Treatment and reuse. All grey water from skins, pantries, and shower, along with black water, goes to our soil biotechnology system, developed by IIT Bombay, which has layered gravel, sand, and active microbial media that treat effluent to a standard suitable for toilet flushing and irrigation. Remaining treated water recharges groundwater. Our waste management strategy focuses on segregation, treatment, and reuse within the campus. Waste is segregated at source into wet, dry, landscape, sanitary, and sewage waste. Organic waste is treated through a biodigester to produce biogas and manure, while dry waste like plastic, paper, and glass is sent for recycling. For sanitary waste, we collaborated with PadCare, an innovative recycling system where used sanitary pads are collected through dedicated bins and processed into reusable resources instead of landfill waste. Sewage waste is treated through STP and reused for flushing and irrigation. A garbage chute system ensures efficient floor-wise collection and transfer for further processing.
Let us now explore the embodied carbon of abstract. Our approach was structural optimization first, material substitution second. Our definitive 75.23% reduction is derived strictly from the SDI carbon assessment tool, which establishes our design intent at a proposed embodied carbon of 1174 kg CO2 emissions equivalent per meter square. How? For structure, using voided slab with recycled HDPE balls dramatically reduce concrete volume. For the concrete, we do per 65% GGBS cement replacement. For steel, EAF steel cutting structural steel emissions by 74%. For finishes, standard vitrified tiles were replaced with polished concrete and recycled terrazzo was used for toilet, reducing emission down over 86%. Yes, our PV systems add an upfront carbon penalty, but life cycle analysis confirms the embodied carbon of the entire PV system is fully recovered in 11 to 18 years through the operational carbon saving it generates.
How about resilience? Is Abstract a resilient building? Yes, it is. Abstract is secured against four scenarios: great failure, extreme heat, seismic events, and water scarcity. Great failure. BESS stores 1650 kilowatt hour, totaling 3 full days of essential systems. Heat wave. The computationally optimized massing shields the interior, keeping operative temperature stable during peak spikes. Seismic. Core outrigger system engineered to IS 1893 Zone 3 to absorb and redistribute lateral forces. Service disruption. 1,37,610 liter of rainwater harvested emergency reserve, giving us 3 full days of autonomous drinking and sanitation for full occupancy.
Okay, so now let's talk about the costs. Vedadnya, our Kirigami module and a perovskite tandem panels brings a capital premium. Yet our financial model projects a 13.3% capex reduction. How does that work?
So, on the civil side, EAF steel has reduced our steel estimates by 19%, while GGBS concrete has lowered our concrete budget by 39%. And the structural system also enables faster assembly by cutting construction timeline by a full year, and interest during construction is reduced from 20.2 million to 11.7 million. We are also positioned to apply for the MNRE RTD grant, which can subsidize up to 50% of our BIPV and Kirigami manufacturing and installation costs up to rupees 60 million, further reducing our capex. Cost reallocation was also done through HVAC right sizing. Our computational design and DSF helps us to drop HVAC loads from 627 TR to 332 TR. This single move has slashed our mechanical equipment costs by 57%. We have shifted the budget from the oversized HVAC to directly into high performance envelopes. So now let's talk about the operational story. The 88% reduction in OPEX. Ashutosh, the math?
So the reduction in cooling load because of the foam is the brief answer to that question. Because our baseline HVAC costs around 14 million rupees annually to operate, out of which 8.2 million rupees is from utility and 5.8 million rupees is from maintenance. While our optimized 332 TR HVAC reduces that maintenance cost to just 2.57 million rupees annually. In addition, our solar system generates a 25% energy surplus eliminating the grid electricity costs and creating a rupees 0.67 million annual utility credit. As the result, the annual operating cost drops just to 1.9 million rupees compared to the baseline of 14 million rupees, hence the 88% reduction. Looking at the full 25 years life cycle, Upstack's evaluated systems cost around 147 million rupees to operate, while the baseline would cost 343 million rupees. This significantly improves the financial performance of the project. The proposed revenue model generates over 268 million rupees annually, with 74% coming from the long-term stable leases, allowing the entire capital investment to be recovered in just 4.4 years.
So Upstack is a high performance engine, creating simultaneous value for multiple stakeholders. For our project partner, it's a grade A asset with a 4.4 years ROI and an 88% OPEX reduction and a net positive future-proof investment with higher asset value and market leadership. While for our MSME tenants, it provides professional and healthy work environments at lease rates which reflect our operational savings. It is a high performance building which also features amenities like sky terraces, co-working spaces, and ground floor retails, which are not accessible at that price point.
I think we are right within the time. So I'll conclude our presentation with a slightly romanticized statement because it's value proposition, right? So Upstack is more than just a building. It's a scalable formula. That's not romanticized. It proves that when architecture is driven by an algorithm, you never have to choose between a profitable asset and a resilient planet. Because in the future of real estate, sustainability isn't just an environmental goal. It is the business model. We are Team Samaved 2.0. Thank you.
Thank you, team. You delivered really well. Let's hear the jury comments and take questions from them. Mahesh, we'll start with you.
Yeah. No, I really like what you guys used, MOO and Pareto. That is the way to go. And I just want to check, when you did this multi-objective optimization and Pareto optimization, did you check actually on all the passive measures like shading devices, reflectivity of the, the paint, what kind of SRI that you have taken, and then checked with, from 0.9 actually to, whatever the numbers, and also the insulation, what is the optimal insulation? So that is a question I have. Yeah.
So the goal of MOO is to get a form which mutually shades itself.
Yeah.
That move alone reduces that moves alone significantly improves our performance.
Yes.
While as you have mentioned, the minute details we have worked on that after the form simplification.
Okay.
So the process is just for to get the form, and then our standard architectural process and sustainability process starts.
Okay. Now, you could have continued the same actually for one is getting the massing, and then
Right.
you could have tried actually for other, selecting a efficient glass.
Right. The
Where-
similar
where-
process.
Yeah. Like what is the right SHGC or right U value? If you increase the U value or if you keep on decreasing the U value, there is a point where it stops. It doesn't work further.
Right.
So these kind of points, getting those.
So I would like to answer that.
Yeah.
So multi-objective optimization and evolutionary solving process works best when there are less variables.
Okay.
Moment we increase more variables, the process becomes complicated and Pareto front becomes difficult for the further optimization. So that's why we choose the specific application of that process.
Okay, no problem. The other thing is you talked about this velocity of 9.1 meter per second. That is, it's too high. So what controls you have in your mind, while designing it?
So in CFD analysis on the optimized form or after the simplification. So we have
You did the CFD analysis
before the simplification, right?
Yeah. The CFD analysis says that the 9.1 meter per second, that is very high in a sense.
Right, so it is indeed very high, but the CFD simulation was done at multiple levels, right? So this particular simulation is on a higher story, but the DSF also helps us prevent the direct entry of the wind as because of the double skin facade and the air gap in between. It also reduces it as well as I feel like in Pune, because of our mixed mode ventilation strategy, most of the time, like the windows will be open. So, and the floor plates also ensure cross ventilation due to the openings on the western side.
Yeah, that is where actually I felt that some kind of a control, because when you're doing a natural ventilation like a mixed mode system, this would have been had. The other one is what kind of cooling system that I'm looking at. There is a reduction of chillers like a sizes.
It's a VAV plus DOS system.
Okay. Now you could have tried with other systems like a radiant cooling system or a displacement ventilation system or any other passive and low energy systems.
So I think the one problem with radiant cooling system is the latent loads. Managing the latent load would become difficult for such a kind of mass. So why we have choose the DOS system, because it's very good with radiant load. Good with latent managing the latent load, because if it's like a two filtration system. Before the air reaches the AHU unit, it filters the moisture.
And just to correct you, Infosys is doing millions of square foot with radiant cooling office building. So latent load can be taken actually with a device system, and the sensible cooling is taken care actually by the radiant cooling system. Okay.
So, great presentation. I really like the way how you guys have like communicated with each other and at the same time explaining us the same in the same format. So I really liked and I appreciate that you have done so many permutation and combination and got to a final form for your building. But as Mahesh was also mentioning that you could have done it with more inputs. So I understand that there is a lot of complexity altogether with that. But I want to point out like once you have optimized it and you got the daylight as 50% for 50% of the hours as per SDA. So you are actually at a very low daylit levels into your flow plates.
So the move was to tackle two things. First one is to the solar SDA, which is the 300 level to achieve the 300 level 300 lux level in the flow plates. And the second part is annual solar exposure.
Yeah.
Moment we increase the VLT value, what was happening was the annual solar exposure was increasing. So that's why we have deliberately chosen that only the north side will have the high VLT value, and inside the core, which is not well lit, will be handled by our smart LEDs and BIMS systems.
So that is right. What I wanted to point out is that
Right.
while you were doing your combinations to get to a form, you have actually excessively shaded the building.
Right.
That is why your SDA is comparatively low. So when you are doing these optimization, you have to be considerate about both the things that
Right.
though you are reducing on the EPI
Right.
by optimizing the envelope, but at the same time you have overshaded the building and now the light is getting in at a lower level. Obviously, you have to provide shading to cut down the direct rays. So you are tackling now ASE
Right.
and you are eventually reducing more SDA inside. So that is the reason. So basically, the final form you are at right now is, as per me, not 100% optimized, though it looks optimized based on the energy reductions, but not as per daylight. So you could have considered that. I understand the radiation and all perfectly, you have optimized it well. But if you are considering daylight, then it is at a lower end because you see a lot of gray area right now in
Right.
your results. And because well-being is also attached to it. If
Right.
the enough daylight is not there, you are using a lot of artificial light and vice versa. Okay. So, but overall, really good optimization schedule you have shown. Another thing, I really like that you specifically tackle the sanitary waste, which generally people don't do it. So, what are you like making out of it once it is?
Those sanitary pads are recycled into a paper for used for packaging.
Okay, understood. Great. And are you also trying to use the energy of the overall waste management once you have done? Are you using that energy numbers also in the reduction? Have you used that in the calculation somewhere?
No, we haven't used.
So I would really appreciate if you can add that also. I think that will eventually enhance your performance even more. Okay. Thank you.
Yeah. Firstly, thanks a lot for the presentation. It was quite innovative and different. And I see how you kind of subtly took our questions that we had put in our D3 and then into the conversation, and you kind of answered those. That was really cool. I still do have more questions for you, unfortunately. So, and trust me, I'm being very nitpicky here because very good presentation. I think a lot of us do agree on that. But I do want to be nitpicky because I want you to guys to know what we're talking about, right? First thing, the easy one out, chiller efficiency. You had stated a very low chiller efficiency in your design. I think you might have updated that. I didn't see it in the presentation, but that's aside. I think because we are on this sheet, I'll talk about this a little bit more. I think you got married to the idea of having the second facade, right? The TiO2 panels and like doing that. I think that kind of influenced the impact on the daylight a little bit more. Correct me if I'm wrong. This is my interpretation, because you've overshaded not just by the massing, but also because of the second fin, right? Because you had to have that much number of panels, and you had to kind of say it's going to improve our indoor air quality. That forced you to have that much amount of panels on that side, and to ensure you get to 50%, you opened up the north. Now what happens when you open up the north is the summer sun is always on the north side, right? You increase BLT, you increase SHGC, then in the summer months your energy consumption is actually higher, right? And while I still appreciate what you've done, I feel the next step would be to try and see how do you make sure that these panels, while they are there, are correlated to how you would design a shading element and integrate a marriage between those two, right? Horizontal, vertical shading you design, you have these. How do you marry those two and try to see you're not getting a dead black space, but you have a combination of, maybe some parts open, some parts not, right? That would have helped you with your daylighting issue. I think that's where, a little bit more effort and understanding. With the technology itself, I'm not very convinced as to, with such fast wind speeds and like you're trying to do natural ventilation, how much time is it going to spend on that panel to really get those, PM 2.5 or PM10 numbers down? That's the technical evaluation that probably everybody needs to do and figure that out. But I think finding that product and trying to integrate it, I really appreciate that. You mentioned about 65% GGPS usage. I don't know where you're getting that number from. Okay. Technical, I mean, at least I have not seen such high GGPS numbers being used. There are lots of implications of that. I'm not saying it can't be done. There are other implications of using such high percentage of GGPS. I would suggest you to go in and like review that number. You also mentioned that cost wise using GGPS was giving you cost benefits. I question that also. Go back and check those numbers. EAF steel, I mean, if you're talking about carbon numbers, there's no doubt about it. Using GGPS or EAF steel definitely will reduce our carbon numbers. But if you're saying that you have 16% or 19%, the slides were going fast, but reduction in cost because of the usage of GGPS and EAF steel, I don't know if that's really affordability. I don't know how those numbers translate to cost efficiency, because steel the quantity of steel reduction in the other cases that you talked about, how you have an innovative encased columns, all of that's really good, and I think that will help you with the cost, but not just material substitution. I think otherwise good presentation. HVAC systems, like how did you integrate? I didn't see any duct shafts and stuff like that with the overcomplicated forms that you have. I think that integration issues could have been elaborated on a little bit more. Um, but thank you.
Sir, I would just like to address the TiO2 panel thing. But from our industry partner, VK Environmental, we got the contact of Toto, who actually manufacture these. So for lab testing, they have actually achieved more than 70%. But then we have reduced that because practical implications might lower that, even dust might lower that. So we have lowered that the cleaning of VOCs and NOx to around 40 to 50%.
Yeah, I mean, honestly, even I had to go research and go back and find where the, Toto panels were being created, done in China, and, the testing and everything. I spent some amount of time figuring this out, right? But I just feel that with the way you're setting it up, again, I question whatever data, even if it's coming from a manufacturer, newer technology, there's always overclaims. But I appreciate the fact that you did take numbers that they showed and they said, oh, this might not be the most optimum, and you reduce it. So I appreciate that.
So I would like to say one thing, that we have what we have majorly learned is that designing is all about finding optimal trade-offs, because we cannot have a form right from the beginning which addresses every issue, right? So even though we have the mutual shading performance, we may have the other issues, like the design always have the second order effect. So designing is actually to addressing those second order and third order effects, rather than just from starting to look for a optimized prompt. That's the biggest learning we have. So yeah, thank you.
Thank you, jury members. Thank you, Team Samavet. Let's take 5 minutes. Our fourth presentation is from Team Mathai. They have worked on a project located at Vanagram, Chennai. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I will stop you and ask you to end the presentation. After that, you will have 10 minutes for a Q&A session. Please keep your answers direct and to the point. All right, team, the stage is yours.
Good afternoon, respected jury members, organizers, faculty, and fellow competitors and colleagues. Wangari Maathai, the first African woman to win the Nobel Peace Prize, inspired millions through the Green Belt movement, in which 50 million trees were planted across Kenya. She believed that it's the little things that citizens do. That's what will make the difference, and that her little thing is planting trees. Our client's little thing is development that is both sustainable and profitable. And now, our little thing is to balance performance with purpose and to design buildings that are good for both the planet and business. Our client discussed developing a commercial project with us on a site in Vanagram. Vanagram is expected to gain greater connectivity through the Madurai corridor and the Phase 2 metro networks. Our client also discussed with us how the pandemic reshaped the way people work. At the same time, rising temperatures, resource constraints, and net zero performance targets are redefining building expectations. So this led us to a central question. How can we create a future-ready office building that satisfies the demands of the real estate market while also responding to Chennai's evolving workplace culture, climate, and long-term sustainability goals? Shut the tower is our response. Our design process was iterative and data-driven. We first started by extruding our site. We then carved breakout spaces to respond to the natural prevailing winds. A climate responsive facade was integrated to respond to the sun, with solar PV systems acting as a renewable energy source. Our design decisions were made to optimize EPI. At the end of our process, we were led with Sharjah Tower, a 10-story commercial development. Our visitors enter the site through a lobby where internal roads lead to surface parking and the basement parking facility. The lobby features a real-time dashboard that displays energy performance metrics. At the first floor, there's a recreational space that encourages collaboration, social interaction, and relaxation. Above, flexible office floor plates have frame views of the Kuvam River and surrounding vegetation. The office floor plates can accommodate multiple occupancy layouts and can also adapt to other uses as Vanagram continues to evolve, extending its asset life. Resourced breakout spaces provide access to fresh air while also supporting occupant comfort. Our terrace garden acts as a green roof and is covered with a solar slope. Indoor planting and low VSC materials enhance indoor air quality while also supporting occupant well-being. Combined, these open spaces provide comfortable 72% of comfortable hours. This is further extended by BLDC fans, which extend comfort to 90% of annual comfort hours. These findings were aligned with ASHRAE adaptive comfort model, with our indoor air velocity being 0.4 to 0.6 meter per second, which is within the comfort range, and we have a PPD of only 8.94. But comfort doesn't begin with the ventilation system. It begins at the facade, which reduces heat gain. Our custom code is integrated with the IBMS, which controls the panel movement. A double glazed inner facade works with a dynamic perforated recycled glass panel, which senses solar radiation and moves accordingly to balance thermal comfort and daylight. This produces a glare probability of just 9%, which is backed up by our ASC analysis done in Design Builder. Our SDI analysis also shows that all our occupied spaces have at least 50% of annual working hours to be daylit. and it achieves 3 lead points.
We adopted a water-cooled chiller system with variable water flow and VFD control fans, reducing pump and auxiliary energy by 30%. Additionally, VAV-based airside control also reduces the energy demand by 30%. Our cooling demand has reduced from 190 TR to 155 TR, while the annual water makeup has been reduced by 80%, accounting to 450 kiloliters per year due to use of VWF and non-toxic chemicals and lowering evaporative loss. Beside energy saving, the system minimizes maintenance, enhances thermal stability, and even reduces refrigerant use by 70%. Operating nearly for 60% lesser hours and using 65% lesser electricity per ton of cooling, the HVAC contributes to 52.3% reduction in energy consumption. O&M plan integrates IBMS and GreenXP analytics to continuously monitor, optimize, and intervention of building performance. It enables predictive maintenance and ensures the building continues under net positive operation condition. Waste is managed through collective segregated system where organic waste is converted into manure and sustainable office practices reduce waste at source. Responding to a site's alluvial soil, we proposed raft pile foundation, where raft distributes uniformly and reduce differential settlement, while 20-meter deep pile transfer the load to the soil strata. Our composite deck slab of 130 mm thickness act as both reinforcement and formwork. This reduces shuttering requirement by 80% and also uses 50% GGBS replacement and 85% EAF recycled steel. This reduces slab weight by 40% and also accelerates construction speed by 50%. Composite slab also has an increased 45% strength to weight ratio compared to other conventional column options. Energy performance. We optimized it through reduce, optimize, and regenerate framework. Optimized perforation densities, solar film, and optimized panel size reduce the heat and solar radiation by 82%. For envelope optimization, we use GGBS and bamboo-crete, a bio-based panel, which has high thermal insulation, high noise insulation, and also contributes to 40% higher strength compared to conventional concrete wall. Combined with low E-glass and recycled facade, our envelope reduces heat gain and increases thermal comfort. For optimized phase, we use high-efficiency systems such as BLDC fan, HVAC water-cooled system, and regenerative lifts, and also IBMS enhance the efficiency of the system and respond according to the occupant's necessity. Cooling demand. We can see the cooling demand for the peak June 3 p.m. is 116 TR, which is well lower than the design capacity of 155 TR. Together, all this strategy, we achieved an EPI of 50.5 per year, which is 60% in reduction. For regeneration, the solar energy is optimized by bifacial gain and 15-degree mounted configuration. For parking canopy insulation, we consider a 20% loss. The grid-tied system powers daytime building operation and exports 12,000 kilowatt of additional surplus among 350,000 generated annually. This is 27% beyond operational demand. The building operates as a net positive commercial office development. Wind and solar energy vary by place, but water has shaped civilization across the countries for centuries. Placed along the Kuvam River, Shaja Tower embraces water as a resource to be conserved and managed. Water performance follows a framework that minimizes freshwater dependency and maximize on-site recycling. The MBR system, waterless urinals, sensor-based controls, and xeriscaping reduces water demand by 47.9% before strategies are incorporated.
The MBS system recovers over 90% of recycled water for reuse, enabling year-round self-sufficiency, even dry period, and additional demand is supported with the storage of rainwater from heavy rain seasons. This reduces sludge generation by 50% and high-quality effluent reduces pressure on downstream treatment system connected to Kuvam. Permeable pavements across parking promote infiltration, reduces runoff, and enhance groundwater recharge while reducing discharge to municipal drainage network and supporting flood mitigation. On an annual basis, on-site recycling and harvesting generate more water than the building consumes, generate a surplus of approximately 46%, and every month is self-sufficed. Thus, our building is a net positive water performance. Thus, all these strategies reduce the water procurement cost fall from 4.2 lakhs to 95,000. Chennai has one of the highest C&D waste volumes in India, and among this, glass plays a significant role in waste stream because it can persist for 1,000 plus years when discarded and unused. Along this, agricultural waste like sugarcane waste, bagasse, and cotton waste, they can contribute to air pollution, carbon emission, and have high impact on human and animal health. Thus, our strategy is to incorporate recycled glass into our facade and multiple application, ensuring that the material doesn't lose its value throughout its life cycle. We also incorporate a bio-based panel, bamboo-crete, which is made from cotton waste, sugarcane bagasse mixed with non-toxic binder on site, which reduces the energy-intensive manufacturing process. Along with this, composite structure, which reduces 80% of farm work and curing requirement, reduces carbon emission during the construction phase. All of these materials are procured within 20 kilometers, which also reduces transmission emission. So our bamboo-crete panel acts as a net carbon negative material, absorbing around 900 kg of carbon per cubic meter. Along these, the recycled content of our composite structure reduces the embodied carbon by 76.7%.
While the above contests like water performance and energy performance talk about how a building can be made efficiently. But we asked ourselves a question: what happens to the building after it reaches end of its operational life? This led us to end of life cycle as a strategy that we propose, stating that sustainability goes beyond operational life of a building. To understand this challenge more comprehensively, we went through a scale approach of component scale, building scale, and future adaptability. Moving on to component scale, our ecothermal panels. Traditionally, the building materials follows a linear approach of manufacturing, using and dispose. But our panels follows a circular approach of recovery, reuse, and recycle. Traditional materials are also generally bound to the structure, making it hard to disassemble. But our design strategy designed for disassemble, making it easier for disassemble. We also use modular panel construction. Material recovery hierarchy. Our bamboo crate materials can be reused and manufactured. Fiber cement cladding, FR reinforcement, and metal fixing used for recycling. And our bio-based core is biodegradable and used for compositing. However, building a material is only half of the solution. But the knowledge about knowing what those materials are, how to recover them, and the documentation plays vital role. Material passport plays a vital role in it. It is a digital record that stores information about the building materials and components. In today's rapid changing world, a building is able to meet the changing demand. That's where our future adaptability comes into place. Our structure is made up of composite structure, which produce high demand as well as the flexible floor place provides clarity and flexibility. Resilience. This project follows a framework of avoid, accommodate, and This project follows a framework of protect, avoid, and accommodate. Under protect, critical building functions and occupant safety plays a vital role. This is addressed by providing energy resilience by including hybrid grid connected solar PV system as well as 30 kilowatt of diesel generator. Dedicated fire staircases and a grid loop sprinkler system is also used to increase the occupant safety. Under avoid, it is used to reduce the exposure and vulnerability of the facade like earthquake, floods, cyclones, and heat waves. Under earthquake, a lightweight structures are used and it is designed for the IS code of 1893. Under flood, raised platforms of 900 mm as well as the pump activator system used for flood resilience. High performance facade system used to create and to manage wind load of 162 kilometer. Heat waves provide high efficient. We are using high efficient HVAC system as well as a passive cooling system to mitigate heat wave strategies. Moving on to accommodate flexible communal spaces, convertible furnitures, and multifunctional areas are used to encourage the social resilience. Collaborative innovation. This project evolves through continuous collaborative iteration between our team members, faculties to provide a solution which is our facade system as well as Green XP, the app. Green XP is a sustainable app. As Mata suggested, it is the little things that makes the changes. Green XP encourages us to provide sustainable activities through app. Having features like energy monitoring, smart light control, automated blind distribution, environmental monitoring, as well as real-time sustainable mapping, which is also integrated with our IBMS.
So far we have seen how the building responds to natural resources such as sun, wind, water, and carbon. But there is one major resource which determines how these resources can be implemented on site, that is money. While evaluating Saja Tower, we begin with a very simple question: is a green building expensive? So, a 20-kilometer material procurement radius, use of recycled glazing, fly ash concrete, bamboo-crete panels, and structural and an efficient structural grid pattern used in reduction of overall construction costs across multiple categories. The baseline project cost was 612.4 million INR. Out of that, 195.6 million INR was spent for services and infrastructure. Rather than providing and adding more systems to it, we focused on the reduction of it through the building through strategies like passive design, material optimization, and efficient planning. These strategies and intervention helped us in reduction of overall construction costs from 612.4 million INR to 537.6 million INR. However, affordability extends beyond construction. The overall reduction of cooling, lighting, and water demand helped us in saving the annual operational expenditure of 11.4 lakh INR per year. Value proposition is not just for the investors, but it is also for the occupants who occupy the space. For investor, it provides a high returns on lower capital costs, lower resource demand, and on-site resource recovery. For occupants, well daylight lit spaces, improved indoor air quality, thermal comfort spaces, and comfortable, flexible recreational spaces help in improving the work-life environment. The Green XP app promotes the users to be an active people to the green environment rather than being a passive providers of the green environment. The result is a building that delivers at every scale. 14% improvement in energy performance, 47.9% reduction in water efficiency, and 76% reduction in embodied carbon, and a strong return on investment on 4.8 years payback period. The future we chose is Saja Tower, a building that learns, adapts, produces, recovers, and evolves for the future adaptability. The future of architecture is not determined by height, glass, and technology, but it is determined by how well a building responds to its surrounding environment. Saja Tower today stands as a vision. Tomorrow it becomes a benchmark for the adaptability. Because the future is not shaped by one grand solution, it is built through thousands of little things. Team Mata's little thing is Saja Tower. Thank you.
Thank you, team. You did a great job. Let's hear the jury comments and take questions from them.
So, congratulations for the interesting presentation. I have couple of questions related to the architecture, first of all. So, you have around 70% WWR initially, right? Like you have the slabs, you have all glass, and then you have a double skin, right? So first of all, what, like, as you can correct me if I'm wrong, with the 70% WWR, you are taking a lot of light inside and a lot of heat, and then you are having a double skin, which is cutting that, and then you are reducing on other factors by having that. So what is happening right now is that you are first letting too much light and heat, and then with the double skin, you are trying to mitigate that. And in that context, you are adding up on a lot of cost, a lot of material, and like there are some thumb rules in the industry, like ECBC says that you need to have at least 40% of WWR. So basically, if you adhere to those kind of things, maybe you could have reduced on a lot of material and cost. Though your number looks too high, but I really doubt the assumptions taken for the cost consideration and for the embodied carbon. Why? Because you are also saying that you have recycled glass, but recycled glass right now is very expensive in the market. It's not cheap. It is expensive than the regular glass you are getting in the market. So have you considered the right kind of costing for that?
So yes, ma'am, we actually source materials from 20 kilometers. We found multiple vendors within this range. So based on that, we also found out that since it is already a developing site, there were glass um, there were glass waste as well. So we're taking that and using that for recycled glass.
So somebody is using your on-site glass and then recycling it to give you a new glass. That is what you are saying.
We are using glass that has been used by other people now.
Huh. So that is what I'm saying, that the cost is slightly higher in the market right now. So as per like your claim in the affordability criteria kind of diminishes it. So that's my take. You can just cross check that at the back end. Then I had another point, which was like on one of the facades, you have shear walls,
Yes.
right? And they are all concrete. So you could have like managed to have other material there and reduced on your embodied carbon on that particular front also,
We
right?
did attempt to use like fly ash and all that to reduce embodied carbon to an extent.
Okay. Yeah, so I just felt the overall the concept and the screen thing is nice, but if you could have just reduced the overall materiality to it, then it could have outstanding like little more standout would have been there.
With regards to like the window wall ratio, we did go with a 45% with bamboo-crete panel as the wall material.
Okay.
So that we have used 45% and we've done design builder simulations with that as well.
So like in the facade, it doesn't seem like that. Where are you using? Are you creating a sill with that?
We'll show you a section. So can you see like that we've used it in the sill and the lintel level now? Is it visible, like the exploded view?
So, what's the height of the sill?
So the office floor height is 3.9 meter now, so it's 1.1 meter.
If you have a continuous band, when you do have a continuous band of glazing, even if you have a sill in the top, and my assumption is it's going to come up to 60%, but you do have like one part of it blocked off. So, I mean, debatable, but the question is, do we want to have a ribbon band glazing wherever it is, right? It's not just the overall window wall ratio number, but also on every facade what it is, right? Overall building, fine, whatever, it could have come down to 45, but on a particular facade, do we need 60% on that wall surface, right? Can you manage to get the same amount of daylight, reduce the heat gain, and reduce the glazing and all of the other things?
We look further.
So I think I'll start taking my questions, and I do want to go back a little bit before the architecture starts, right? Siting is everything. You talked about the Kuam River and how it's traditionally important, and I did a little bit of research and know that it's a very urban river, a lot of pollution, this and that, whatever it might be. But I see your building edge is only 13 meters from the edge of the river, right? Local codes, NGT codes, does that follow the codes? Does it meet the requirements? Because I think 15 meters is the minimum setback you need to have. You seem to show only 13 meters, right? That's a big flag, a red flag for me. And I saw that you talk about a little bit of a plinth, but you have a basement. You have services in your basement, including your BESS battery systems, right? If your river overflows, your basement's going to get flooded. One of the major important things about resiliency is to understand what are the site constraints or what are the impacts of calamities are existing on your site, and how do you mitigate or how do you work around those things. Appreciate the fact that you have a best system and you have a DG, and you're saying we can stay for how many, or 2 days, 3 days of grid free thing, but if you have a system that's in the basement where it's that whole river floods, right? You can't have it in the basement. That's a no go, right?
So regarding the river's level, the base of the basement is 3 meters above the river's level, so like the water level.
So urban flooding doesn't really happen with the overflow of the rivers most of the times, right? There are channels, and then if a drain gets blocked somewhere, right, flooding is going to happen. The river's already full capacity, right? So urban flooding, typically, if you've seen in cities, it's not really like, oh, this is the river and this is the edge of the river, and that's why the flooding happened. The whole what do you say? The area around gets saturated. Your drainage systems are not perfect, so that's where flooding happens, right? And if you know that you have a river system that floods, and then all of this, I wouldn't put my services in the basement first thing, right? And there are rules and things about how much distance it needs to have. I don't see you meeting some of those issues.
So that regarding the distance, sir, so there is our 8-meter setback. After that is a
5 meter, 5, 6. Okay.
6-meter road, and after that there is like a small bund, sir. So totally it takes like 16 meters.
Okay.
There's a bund between like the road and the river's water.
Okay. So again, nitpicking, but I think that drawings were not very clear, right? It was not quoting the correct requirements, because see, if it was not beside a river, I wouldn't have gotten to all of these issues, right? And I'll get into whatever your systems and things that you're looking at. I think, like again, like she mentioned, the window wall ratio. I understand that you have actuator systems to kind of move these things, very innovative. But what I do want to understand is these kinds of systems do have a qualitative problem, right? When you have opaque systems with holes in it, it's going to cast shadows, and these shadows keep moving. Very distracting for an office building. Very innovative or very nice when you have like lobby or hub spaces or like where it's not active work, right? So I don't know if you did a qualitative analysis of how it changing patterns and through the day, or how that's going to affect. And the costing of all of these things, you said 20 meters sorry, the distance 200 meters, or the materials procurement. Yeah, so some of these actuators are not available in India, and you seem to use it all over the facade, right? I would have, if it's an innovative technology, I would optimize where I'm using it also, right? So east and west obviously are difficult facades to kind of deal with, and where operable systems are the most efficient. Otherwise, with fixed systems, you can't work and ensure glare-free spaces. So I would not mind using it on that, but on other facades, not. I would go with fixed to reduce on the costing and all of these technologies. Uh, so and the U values and stuff that you had shown, at least when I looked at the report, it seemed like it was not even meeting code. Uh, but I don't know if you've revised it and figured those things out. But I feel like overall concepts there, but like plugging it into ensuring that you're meeting codes, or you're um, you're looking at it the overall picture. I think that's something you need to
With
kind of figure.
regards to the facade on like the north side and the south side, so we found that the north side in the months of May, June, and April, in the summertime, that's where the sun is really hot. So even in Design Builder, when we were going through our iterations, the western core iteration proved the highest, and then the northern core actually proved the second highest. So that's why we went with the northern facade as well, the kinetic.
Yeah, I'm not saying you should not shade your north facade. I did mention it to other people also that, when they had the north open, I said, no, you should not keep the north open. What I'm saying is a choice, right? Do you want to go with an operable system where a fixed system can work as well, if not better than an operable system? Why do you want to bring in more technology, more complexity when you can do very well with a fixed system?
We've used less amount of panels on the north side, sir.
No, right.
So regarding the innovation for the facade, we have taken inspiration from a sliding window. So the actuator that's used is a basic one which we use for a sliding door. It's just a BLDC motor which we can get easily in the site under 20 kilometer. The basic one that we usually use for a sliding window or door, that BLDC motor is what we are using. And regarding the envelope U value, earlier we have given only for the concrete. We haven't talked about all the GGBS replacement and incorporation of bamboo crate. So for that, it's under ECBC compliance. ECBC says it should be below 0.4 and ours is 0.44. That's also 0.45. So ours is 0.44.
When you're talking about embodied carbon, right, it's not the final vendor who you're buying it from, but where the material or the motor is manufactured also. Embodied carbon, there's a lot more. There's a lot of story behind it, not just the vendor where you buy it off of. We can have this conversation later.
Yes.
Hi. The overall the presentation is good, and on the water section, I really like the the water calculations. As Vaisali was suggesting, what I found the descriptions is that in terms of the heat gain, envelope heat gain, it is coming to 48.6 watt per meter square. So actually, if it is a most efficient, high performance, thermal performance facade, it should have been a 10 or a 12 watt per meter square. So that is where I think whatever the consideration that you have done, it's not been simulated with this, because the envelope heat gains actually is very high.
So the heat gain intensity, it's just not the envelope heat gain. It considers all the equipment and occupants heat gain also. So we used Carrier Hab software to calculate all this and came up with a result of 155 TR. It just doesn't involve envelope heat alone.
In your report, you have mentioned that 48.6 watt per meter square as an envelope heat gain. So that is where I was.
We have just said it's a heat gain intensity. I'm not sure whether we have said envelope anywhere.
Okay.
I might
The
be
envelope
wrong,
heat gains is basically the heat coming from the facade, the roof, and the facade.
So this is based on occupancy and equipment also. Internal heat gain is considered and it's done using a HAP carrier software.
No, you will not get that in the. Did you do the energy modeling? Which software you used?
We use carrier HAP. Our consultant helped to simulate the result, and this is the floor-wise results for that. So
And the other one is the MEP cost it was an higher side. I think you should have had a MEP consultant, working with your team to get the casting right. So that is my observations. That's it. Thank you.
So there was in your reporting, right? There was some inconsistencies in trying to understand what kind of systems you're using. Some places you mentioned concentrate volume we are using because it's easier to maintain, easier to run. When I looked into what specific sy- systems you had installed, they was talking about VAV controls. So just a little bit of inconsistency in on different sections and different places what you were talking about. So some of that was also a concern.
so this is for future adaptability. It means whoever coming for the rent, even for the office or in future, whether it's gonna turn into a library or a community hall, we might not know the demand at that time when they have the partitions and all. So from the AHU, we have a CAV connection, and from when the building is rented out, that time based on the zones, we will be giving VAV controls there.
Yeah, I mean, I think the conversation go too technical, so we'll just leave it at that. But there are some inefficiencies in the way the system was outlined. So like Mahesha said, maybe talking to your consultants a little bit more and fine-tuning what narrative you're putting together will help in, improving the numbers that you're showing us and the reporting that you're doing.
So I have something to add. I mentioned in one of the comments that the control integration and the loads you have considered for dynamic facade has not been considered in the EPI calculation. Have you worked on that? Because obviously there will be a good energy usage with the dynamic facade controls as well.
Okay, please repeat the question.
So I'm asking that did you implement or add the energy usage which is going under the screening of your systems, like your dynamic systems?
Like the energy consumed by the facade movement?
Yeah.
So yes, ma'am. Actually, every 15 minutes, the facade senses the environment, and based on that, it acts. So we saw that every 15 minutes, approximately, it moves for like 20 seconds. So every day, one single panel consumes approximately like 5.5 kilowatt per day, and totally we're consuming 1,200 kilowatt per day on an average basis.
Earlier it was not mentioned in the EPI calculation. Have you added that? Have you considered that energy usage in the EPI calculation? That is what my question is.
Yes, ma'am. Yeah.
You have
we did.
considered.
We have given it along with the BMS and other equipment. So we haven't mentioned it separately, but the total it's part of the equipments and BMS.
Okay, thank you.
Thank you, Team Matai. Thank you, jury members. We will now take a long break for lunch. We will start the presentation for Team Solage at 2:30 p.m. Folks online, I request you to tune back to this channel and be ready for the presentations of the upcoming teams. Thank you.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world's so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. rolling so high, high, high. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so high, high, high. We're making it cool, cool, cool. We're from SDI, net zero through and through, through.
Now continue with our presentations. Our fifth presentation is from Team Solage. They have worked on a project located in Raipur, Chhattisgarh. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I will stop you and ask you to end the presentation. After that, we will have 10 minutes for a Q&A session. Please keep your answers direct and to the point.
Good morning, one and all present here. Our team Solage would like to present a project Saksham that was in partnership with Raipur Municipal Corporation and Space Architects as our guide. We tried to do the building. We would like to introduce the whole project initially with a short video to give a glance of the project. Sound isn't.
Rapid population growth is accelerating urbanization across the world. As more people move to cities for jobs, education, and better opportunities, urban areas are becoming increasingly crowded. However, the amount of land within cities remains limited. To accommodate growing populations, cities are expanding vertically through high rise buildings and dense housing. This rising demand has made urban land one of the most valuable and contested resources today. When we look at this density, we realize a fundamental truth. The future challenge is not just energy generation, it is space. Every single square meter in our cities is becoming heavily contested. Buildings shape cities long after construction ends, making commercial offices one of the most impactful typologies we can build. Recognizing the potential of underutilized urban land, the Raipur Municipal Corporation aims to transform barren government plots within the city into drivers of economic growth. We undertook the challenge of designing an office building that not only activates the neglected site but also promotes sustainability, balancing economic viability, social impact, and environmental responsibility. Imagine Old Raipur, crowded, sweltering in 45-degree heat, and centered around an abandoned plot. We are transforming this empty space into a living net zero building. To solve a local economic issue, we combined affordable retail with premium offices. The high-end office rents pay for the affordable shops below. This guarantees a fast 4.36-year payback for the developer while helping local vendors thrive. When you compare this to development in sprawling Tier 1 metropolises, Tier 2 cities like Raipur face unique challenges. They demand budget-conscious, highly localized sustainability rather than expensive imported green tech. That is why we leaned into regional agricultural waste, collaborating with researchers to develop rice husk ash bricks and insulation panels that slashed our embodied carbon by 78% without breaking the bank. Getting to this finalized vision was a rigorous 6-month journey. Starting in late 2025, we assembled our multidisciplinary team, secured the Raipur Municipal Corporation as a partner, and conducted deep site analyses. By January 2026, we had finalized our passive strategies and validated them through extensive energy simulations. Over February and March, we worked closely with our industry partner, space architects, and faculty members to refine our structural components and finalize the floor plans. This iterative process allowed us to confidently submit a fully optimized net zero commercial blueprint ready for real world construction. But more importantly, every step of this journey was driven by one goal: to make our project truly Saksham. In Hindi, Saksham means capable and self reliant. By designing a structure that generates its own energy, recycles its own water, and funds its own community impact, we haven't just designed a building. We have created a fully capable, self reliant ecosystem.
Moving further, listening to the city, our site is located in Raipur, and the project, how we started it with was initially there was already an existing Raipur municipal building there. They relocated it to a different location, and based on that, the tender was issued for this project. We moved further with so basically our project, the overall site area is 2100 meter square with an FAR of 2.71 as per the Chhattisgarh code. The site, as you can see, has a Jaistham Chowk at the core of it. It has two main roads, one 24-meter road and one adjoining to it is a secondary road that is 4-meter road. The road has a lot of street and food vendors. So we have tried to relocate them into our site as well as provide pedestrian entries to this site because there is no vehicular movement within the site as there is a parking facilities provided within the 200-meter radius of it. So the site things. The site receives prevailing hot winds from the west as well as from north east. We receive the winter winds, and the site receives a temperature of 30 to 45 degrees Celsius with an rainfall of 200 to 400 mm. Whereas the humidity during rainy season peaks up to 70 to 80%, and during other duration of the year, it's around 50%. Building the envelope, we moved further like our envelope started with a basic understanding of the site because like a site has a constraint in terms of the orientation can only come in north-south direction because of the site constraint. So we have considered the existing tree, sun path, wind, and the ground coverage to develop our form further. For this thing, we tried 3 strong iteratives to make sure that we ensure the thermal efficiency to derive at our final design. As we were not able to orient our building in east-west direction, we have provided multiple facade treatments. To the east, we have provided custom louvers to make sure that the daylight enters properly as well as restricting the solar thing, so thermal stress, as well as we have provided deep recessed windows as well as metallic frames for on the west side so that the hot prevailing winds can be cooled as well as shading can be provided. We have also provided thermal breeze blocks at the west side of this thing. There are also planter box on the south as well as the east side of the envelope. Looking at the site plan, you can see 2 entries, one at the front and one from the secondary road. The trees have been considered which were existing on the site while designing, as well as the central courtyard acts as an ecological element of our project as it has permeable pavements as well as the tensile structure that actually collects rain and helps it to penetrate using retention feet. This thing, This is the basement plan, which occupies most of our water storage tanks, including fire, rainwater harvesting, grey water, etc. The Raipur also has a resilience issue of flooding, flash flooding. So we have provided water collection tank for that as well, and also for the future expansion tanks are also provided. For the ground floor plan, in the vertical zoning, we have ground floor as the eateries, which is public zone. You can see the purple, the red is the corridor, blue are the vertical circulation of the site. As well as on the second floor, we have on the first floor, we have shops, which is again public spaces on the site. On the second floor, we have co-working spaces, which are semi-public zones. On the service floor, we have provided majorly storage rooms, BMS, HVAC, fire control rooms, etc. Moving further, from third to sixth floor, moving from third to sixth floor, this is our office, small office area. In this, we have provided common breakout zones at the center of it, and seventh and eighth floor has the large office areas. These are fire safety and the roof layout for the solar PV, which we have used for energy generation.
Yeah, these are structures. Yeah, actually, in the base case, we have taken the conventional plan, the structural plan, which is like they are using the maximum amount of materials and everything. In the proposed case, we have taken the optimized all the materials and everything structures. So this was done by our structure engineer, and it was done in StatPro and everything else. Yeah, by optimizing structures, we have reduced embodied carbon as well as even the cost and everything else. Yeah, this is about innovation, collaborative innovation. Yeah, actually, Sarabdeep Gupta there is a ISC faculty, so he has been researching on this. We have taken his inspiration and we have talked with him. So he just told that whenever we are doing the riser cache, we just need to do the trial and error method till it comes. So we did few trial and error methods. Then industry partner helped them what all ratios we can do. So yeah, we have tried few trial and error methods when the faculty has said us. Then yeah, this we have done in our Kharagpur. Actually, we thought of bringing it as our leader. Actually, our team leader was hospitalized in, so we didn't bring these materials. Yeah. So these samples, you can see that these are different ratios. First sample was when the faculty told us how to mix and all those things. Then later on, we tried few things, and in few it didn't work out very well. And then industry partner tried, and at the end the sample was kind of it was coming. Then we sort of adjusted with few these thing ratios. Yeah, even we have taken the insulation in risers with the risers. So because XPS and even EPS, these are emitting few carbon emissions. This can be reduced further because the risers material is largely available in the Raipur. Yeah, this is one more innovation we tried, which is rainwater catchment, and as well as whenever we are trying to innovate or collaborate something, one system is not acquiring to only one solution. It is trying to solve multiple solutions. For example, whereas if you take this thing, rainwater harvesting system, so this is not only collecting the water and everything else, it is also giving the shading, and also it is providing sustainable all these things. Yeah, next.
Coming to the energy part, this is the energy demand of the building. How we reduce the energy demand of the building from the base case from 234 EPI to 85.5 EPI. If this is a design case, 85.5 EPI. With the shade, we got 207, and with the DOS, with the dedicated outdoor air system with gate 134, and with the STS panels and night flushing, we got 85.5 EPI. These are the control systems to reduce the energy demand of the HVAC. This is the optimized energy consumption, lighting achievement. The density of lighting power density is 1.34 watt per meter square, and 73% of reduction in light power density These are the comfort with the less energy. The cooling set point temperature here is 24 degrees Celsius, and annual comfort hours is 8,715 hours per year. Unmet hours is 45 hours per year. This is the transmission distribution, and those are BMS and EMS functions. Coming to the assembly part, roof assembly is higher. Overall heat transfer coefficient is 2.59. When the heat transfer coefficient value is higher, the heat transfer also higher. So it is by using this assembly part, we get 31% reduction in heat transfer. For external wall assembly, we got 87% reduction in heat transfer. For internal wall assembly, we got 81% heat reduction in. For window assembly, double glaze window glass, if a U value is 1.0, 1.8, it get around 71% reduction in heat transfer. These are four are positive design strategies to reduce the HVAC load. These are the effective positive strategies to office environment. Without these positive strategies, we get overheated and unproductive. We are exposed to direct solar heat gain, sweating and fatigue. With these passive environment effects, we can increase the productivity of the office workers. So this is the comparison between the HVAC system, different HVAC system. CAV system and CAV means constant air volume system, and unitary system, VAV variable air volume system, and VRF variable refrigerant flow system. Under this is the HVAC optimization by the shading part DOS system. We got a reduction in EPI reduction 64% and 38% cooling load reduction. LPD reduction is 56% and EPD reduction is 47%.
Until now, we have been discussing about saving energy, saving water, and reducing carbon. So,
yeah, now we are coming into water thing. So, water we have achieved the actually in base case we have taken 8,500. This we have taken from the NBC norms, where each thing as like visitors we have separated, and even the restaurants we have separated, and remaining all as per URDPFI we have taken 45 per liter. So that was the base case. So we have reduced nearly 48% by efficient fixtures and all those things. Then we thought of that even efficient fixtures won't help us. The recycle process and cyclic loop is mandatory. So then in HVAC, almost 85 to 90% the whatever water is there, we are recycling it and we are using it in that. So for non-potable purposes, we are using those things. So let's and one more thing, yeah. Harvesting, rainwater harvesting, and even the recycle thing is meeting our water demand. So it's for us, it's net zero kind of thing. Yeah, this is carbon. In carbon, we are taking the in base case and proposed case separately. In base case, we went through the conventional structures thing. The 70% whatever you are seeing, that it's not the same things, like same building and etc. things. In the base case, we have taken the conventional structures, conventional plans, conventional layouts, and all those things. In all those optimizing thing, the proposed case we have done. And all the values you are seeing here, we have taken from the EPDs. Yeah, these are the EPDs, which there are official websites. So from the EPDs, we have reduced all these things. It's like there are 5 parts of whatever is there is given: wall, fenestration, and floor, and all those things. Yeah, this you can see that how we have emitted less from base case to proposed case.
Okay, so when we think about sustainability, we always think about solar panels, but we think sustainability starts from a very early stage. So whenever the sustainability, we think over the building, but we think in terms of people. So we check on the color psychology of the paintings, and we think about the ergonomics of the designing of chairs, working spaces for the working people, and the informative universal designs, which is like helpful for the working peoples. And then all the structural buildings where they measure air quality, but we think about improvising it. So we have various strategies to improvise it, and we have even specifically picked up internal plans which would help us in this strategy. And then so we mainly focus on having a natural daylight from the sun, and we reduce the glare from it with strategies at which we are structural strategies which we are using, so that the glare is reduced from it and we are utilizing the sunlight to the max. And then we are not fighting with the climate, we are just collaborating with it. So we use the natural ventilation at the period from the July to February. So at the period we won't be using HVAC, and we'll be maintaining the natural temperature and good ventilation over there. And during the peak summer season in the Raipur, where the sun goes very hot, at the time to check on the people's comfortness, we keep it at the temperature, average temperature around 27.5. And these are thermal shock strategies which we are using to have a good ventilation over the building. And then yeah. So, and our legacy continues to central courtyard, terracotta bridge block. All these things are our unique points that which helps us in having a good ventilation over the buildings, and which the EMS and BMS, which helps in quality utilization of electricity and the energy over there. And market and value propositioning, we set an example as an Indian people, that we set to the market, we set an example to the market by having good employment strategies to fight over the various temperature variations. And
To stop you there, thank you, Team Solage. Let's hear the jury comments and take questions from them.
So, nicely presented. Thank you so much for that. I really appreciate how you have actually considered the review comments and tried to bridge that gap in your presentation. That was clearly visible. So, highly appreciate that. And in the overall design, I really like the fact that you have done the operative temperature calculations and graphics, which were clearly demonstrating that you were able to optimize on the thermal comfort and about the interior design and daylight coming in inside the building. That is also highly appreciated. So I have few questions regarding the EPI reduction. So you said that there is a 64% EPI reduction. So somehow the base case again was somewhere around 250-ish or 280. So have you considered the similar area specs related to it? Because the overall reduction seems little hypothetical right now. Have you cross-checked on all of those numbers?
Yes,
Yeah.
I consider the area.
And would you like to explain what you have exactly in detail done for the HVAC?
In HVAC.
Yeah.
HVAC we are using VRV system. Hello.
Yeah.
In HVAC we are using VRV system. It is the best one from the graph it is shown
Mhm.
from the analysis part. So
But there
it's
is-
the DOS system including the part, and we are using also evaporative cooling with outside near the condenser to run the efficient HVAC system.
And one of the other thing is that in our building typology, our area more than 50% is having an AC, HVAC system that is there. So because of that, our base case is so high. And like later on, when we are reducing it to 85, we are actually achieving a super ECBC norm that says we have to achieve around 67% when your area is more than 50% in terms of HVAC.
Okay. So in terms of affordability, I wanted to understand that what was your exact approach in terms of material and the costing you have estimated in that case? Because the numbers looks on the higher side when you have considered it in the to create the overall estimate and difference.
So in base case, we took the more columns, the whatever conventional layout we will get. So we just asked the RMC or else whoever in the Raipur. So we just took the column layouts from them, column layouts and beam layouts. Let's just see how are they going to design and what is the maximum, how are they going to design, how our materials are used. So in that case, we have just used it. Then later on, we have hired, like we took structure engineer in our campus. So then we optimized all the calculations and even columns and beams. That's how we reduce that's how there is a huge difference between the base case and the proposed case. It's not the same for everything. So
So you mean you have reduced on the structural design and then based on that.
even in the slab, we have used the hollow slab and even waffle slab. So even though the concrete and cement got reduced by it.
The bricks we are using is what we have synthesized. The properties are same, and the cost is like very much less than the one which is already being there in the
And the
market.
U values are tested for those?
Yes, it is tested.
Okay. Thank you.
The overall presentation is good, and I have few suggestions, not really the comments. This this is a east-west orientation building, right? So it's good that you have designed a deep shading devices. My proposal actually would have been, what if you orient the windows actually towards north or south, at an angle.
We thought of proposing it in the east that the windows should be oriented towards the north, but it was kind of the structural load and all those things were not even in D1. If you observe, in D1 we were proposing that angled windows, but when it come to D3, it was somewhat structural. Engineer said that let's at least go with the eastern lowers and angled lowers. So that was the optimized one. That's what this was.
And you could have achieved the daylight. Because the east-west orientation is very
Even with the vertical lowers, we are getting the diffused light inside the building. So,
but at a low angle, it's very difficult to get the you'll whatever the shade you will sun always be there.
We'll look in.
Yeah. Other thing is that lighting 1.34 watt per meter square. I think that looks very too low actually for me. Maybe.
So actually, we calculated the lux requirement for a place, and we, to the extreme, we managed to have it with LED lights, and we just like compared with the original prices in the market, and we have our spreadsheets presented in D3, and from the base case, it is like the LEDs like right now is like being so watt efficient, so that is helping us to reduce the lighting loads demand.
Understand, but that is I since I'm not using those lights, but what is the lumen per watt you are using? Any idea about the LED lights that you used to get that? You need to have an extreme lumen per watt for the light, to efficacy of the light.
So actually, we just had an lux which is needed for a room. We had a numbers that which is required specifically for that, and we calculated the angle that to which the light gives the lumens that we needed, and then we decided it. So
No issues. I'm saying that you have to look at it.
thank you, sir. We don't.
Another one, this in the water you have taken 95 LPD. I think hope you have corrected. In my comment also it is one. For office building actually in a base case is only 45 liter per capita.
Yes.
Then it's very difficult to control the glare also because of the east-west wind. So that is the challenge. Then it's very difficult to get the daylight. The comfortable. Other suggestion was we could have used this EN standard for adaptive thermal comfort to improve the the temperature actually could have increased from the ASHRAE, and then you can also reduce your operational EPA. So those are
actually
the
we did few trial and error methods in the Rhino, so that's how we went with that angle, daylight and everything else. So it was only with the EPW and everything else.
Sure.
Yeah, so I think overall a good effort. I think the process that you took to try and achieve where you wanted to go, I like the process. Um, but I do have some comments with, please take it constructively. Uh, so the first thing that you kind of mentioned was there's no vehicular access to the place. Was it a design choice, or was it you didn't have access to the site? Because I see a large vehicular road, like 24-meter road, and there is also another road. Is there a particular reason why you did not allow the vehicles to get into the site? Was it a
Sir, so basically, the issue was that we had a site very thin, one narrow. We had site that was very narrow. Firstly, secondly, there were a lot of parking spaces provided within the vicinity that can be used as suggested by the client. Because we suggested this problem with the Raipur Municipal Authority also, that this is the issue, that we feel that vehicular circulation would be very difficult in the site, and it will, like, the other services and those places would not be able to incorporate. So that's why we did this.
Yeah, so there was no clarity in how it was presented, right? If it's a design choice, you're telling the client not to do it. That's a good, yeah,
That's
right.
what
But
that was the client.
the narrative, in a lot of places, the way the narrative is written was not super clear. On the HVAC system side, I wasn't very clear in the D3 at least whether it was a VRF system or whether it's chillers. Now I hear it's chillers, but again, just that the clarity in end to end when you're working with your consultant, they'll give you a lot of options. There's a lot of new terms that you will learn, but you can't just paste them randomly. It needs to be coherent. It needs to follow through. High side, low side, everything has to fall through and be consistent. Otherwise, for as a reviewer, it's very difficult for us to figure out what you're actually talking about. And you in one of the slides you said there is an EPD reduction that was accounting for savings and the energy.
EPD, yes, for carbon.
But that was on the energy slide, right? Where you said lighting reduction, cooling reduction, and then you said a EPD reduction. So EPD is equipment power density, and you assumed a reduction. How did you assume a reduction in the equipment power?
Using the pie stars.
So for equipment, basically we started with a base case, whatever we had initially used it and what we have seen in the office building. And then we moved further by using 5-star rated equipments, and what are other alternatives that are there. They were a little bit higher in cost, but they were reducing the energy consumption to a great extent. So we changed that. Also, sometimes like we see a lot of number were also altered in some of the cases where, say for example, the one floor or two floor had more equipments. We considered with a human alternative. Say for example, cleaning that could be altered with a human or some other possibilities.
Yeah, typically EPD reductions, when we're looking at it, I understand where you're coming from, but we don't really look account for it that way. But I take your point that it does, you can look into it that way. One of the major things in the presentation today also that I noticed in the previous reporting also was that you had a lot of AI generated images, right? But when you translate that to what you mentioned, there's not a one-to-one correlation into what your drawings are showing and what those images are showing. Conceptually, they're same, right? But they don't match each other. There are also, some places where you've mentioned, the windows are oriented that way. And then I think now I understand that in D1 you had that, and in D3 you changed it, but the narrative still seems to, or the drawings don't seem to still match in certain cases. So while you make those design changes, it's important that you consistently upgrade your, narratives to make sure there's no confusion. And I mean, daylighting analysis and all of that, I think you should kind of tighten up a little bit. Also, there were like things like when you mentioned organic composters and that they generate biogas. Uh, these are small terminology concerns, right? When you say a composter, it just produces manure. If you want to generate biogas, it's a different technology. So while you're exploring different aspects of systems and technologies and trying to integrate, I know it's a whole lot of things, right? And I really appreciate you guys taking a effort to start learning from what a U value is to go into very advanced HVAC systems and doing energy models and everything. But at the same time, I think a little bit more effort to try and make sure that whatever's being presented finally is vetted. Please take help of consultants. That I think more and more people are coming and helping you guys out, and you are in a great place to find that help. So that should be good. But yeah, overall, I think I like the process that you took, the form and everything. It kind of does make a lot of sense. The rainwater harvesting systems that you use. Yeah. Thank you.
Thank you.
Thank you, sir. We'll look into those comments and we'll revise our things and make the design better. Thank you.
Thank you, jury members. Thank you, Team Solage. Great job. Let's take 5 minutes and get ready. from Team DOT. They have worked on a project in Anna University in Chennai. Team, you will have 20 minutes to present your work to the jury. At 15 minutes, I will ring a signal like this. You won't have a 21st minute, which means at 20 minutes, I will stop you and ask you to end the presentation. After that, you will have 10 minutes for the Q&A session. Please keep your answers direct and to the point. All right, team, all the best.
Good afternoon, all. We started with a question. Imagine a young researcher arriving at his office. Throughout the day, they move between discussions, simulations, problem solving, and innovation. Yet, the office around them consumes excessive energy, relies on external resources, and often disconnects people from the environment and one another. We asked ourselves a question. What if the building itself could become the research partner? What if the building could actively support innovation while demonstrating sustainability, resilience, and performance? And the solution was CHIRP, Chennai Innovation Research Park. Today, rather than presenting the project, we would like to share the story behind the scene. The site challenged us. Anna University, one of our prestigious institutions in Chennai, is our project partner. We were given a 2.29-acre site inside Anna University campus. The site offered tremendous opportunities, vibrant academic ecosystem, mature vegetation, strong research potential, city-defining landmarks, and high connectivity. Yet, it gave challenges as well. High solar radiation, humidity, flash flooding, existing vegetation, and we had an existing RCC bed. Here, we had a choice to design despite of the site or to design with respect to the site, and we chose the latter. And this is where the story begins.
Understanding the problem was only the beginning. The real challenge was deciding to respond. From the beginning, we decided not to design first and evaluate later. Instead, performance became the driver of every design decision. Architecture design. Our climate analysis guided orientation, massing, shading, ventilation, and thermal comfort strategies. The concept evolved from the site. The central banyan tree was already performing many of the environmental functions. The tree became the protagonist. The building masses evolved around. Volumes were fragmented and strategic voids were introduced to reduce solar exposure, to improve daylight penetration, and enhance cross ventilation. The courtyard became the environmental and social heart of CHIRP, strengthening visual connectivity, informal interactions, and connection between occupants and the nature. Vertically, the building follows simple and efficient zoning strategies with respect to functions. Looking in detail into the plans, site level, entry and exits were positioned on the southern edge for efficient circulation, and services were consolidated along the northern east for easy access. The ground floor plan, primarily dedicated to the still parking, and houses building management and related spaces. The first floor accommodates the cafeteria, with which visually and functionally connects to the courtyard. The second and the third floor follows a typical layout, primarily of office spaces. However, the second floor features a breakout space on the southeast side, providing an informal area for relaxation. For cooling, we adopted a Moving on to engineering and operations. Through our evolution of alternative cost construction methods and guidance from our industry partner, Nanda Green Associates, we adopted a high-performance steel structure system. The system enables larger span, column-free interiors, reduced dead loads, greater flexibility for future adaptation. To ensure operational influence, all major systems are integrated through a BMS, Building Management System. Our industry partner, Innovil and SmartLink Private Limited, helped us understand the logistics, components, and the methods on how they can be integrated.
For cooling, we adopted a variable water flow system using modular air-cooled chillers, variable pumps, buffer tanks, fan coil units. This strategy reduced refrigerant dependency, improves efficiency, and provides operational resilience through modular redundancy. Resource management extends beyond energy. Waste management at site follows a simple principle: segregation at source, recycle wherever possible, and ensure certified disposal of specialized waste streams such as the e-waste.
Innovation. One of the biggest lessons that we learned through this competition was innovation is not about creating complexity. It is about giving simple solutions. Through discussion with our industrial partners, sustainability experts, and our simulation analysis, we have come up to 3 major innovations. Our first innovation is the structural circularity, 100% bolted steel connection system, where 60 to 70% are recyclable. Our second innovation is the Soul Whale wall. It is a self-shading pattern wall where this texture facade system designed to minimize the direct solar exposure. This tapered brick arrangement allows minimal heat radiation to enter to the interior, promoting thermal comfort to the users. Our third innovation is the movable bamboo shading fins, where the bamboos are attached to the metal frames and with the use of pivoting mechanism, and this, with the help of the railing, it is movable. It is a tri-benefit performance model where it gives 3 major benefits. It blocks sun radiation, improves the ventilation, and maintains visual connectivity. The next is health and well-being. In health and well-being, we have covered 3 major things: indoor air quality, thermal comfort, and visual comfort. In indoor air quality, IAQ sensor network, which is integrated with the BMS sensor, continuously monitors the indoor environmental quality. The thermal comfort is followed by the passive and active strategies, where it is done by providing conditioned spaces, mixed mode, and naturally ventilated spaces. And then the visually comfort spaces are daylight responsive design and glare reduction strategies are done. These simulation strategies are supported to make the spaces more productive and well-being. Energy performance. So instead of going for simple solutions, we have followed strategy-based EPI reduction. So climate responsive form optimization, energy performance envelope, external shading, low E glazing, efficient HVAC and MEP system, solar offset. These things helped us to reduce the EPI. After reducing the EPI, the energy dependency, then we looked into the solar renewable resources. We have gone for bifacial solar panels by applying high SRI coating on the terrace. This increases the albedo effect. Thus, it improves the efficiency of the solar panels. This is the Vare type bifacial solar panel, which is 630 watt peak, and it is 22.2% efficient than the conventional solar panels. And the solar PV system is supported by the inverter, smart net meter, and then the surplus energy is sent off to the utility grid and taken when it needed. And these simulations were resulted in our EPA reduction. Then the water performance. By using efficient fixtures and aerated waterless urinals and vacuum WC, all these strategies helped us to reduce the water usage from 45 LPD to 14 LPD. And this reduced 68% from the base case. And then we use nano ultra purification system to purify the rainwater for the potable purposes, and that gives the efficiency of 85%. And the MBBS system gives the efficiency of 90%, which purifies the grey water, and it will be used for flushing, landscaping, irrigation, and VWF systems. In the site level, the storm water is sent off to the bioswales, which will help to percolate to the groundwater recharge.
Beyond operational efficiency, we also focused on reducing the carbon that is locked into the building from day one. Our next focus area was embodied carbon, where the material selection played a critical role in decreasing the building environmental impact. For the building envelope, we adopted AAC block in replacement of conventional brick masonry to reduce the material consumption and improve the thermal performance. Structural framework utilizes steel with composite deck slabs, enhancing flexibility and future adaptability, further reusability and recyclability. High performance low E glassing containing 20% of recycled content was selected to improve energy efficiency, while red oxide flooring was chosen as a durable locally sourced material. Additionally, the demolished RCC bed on site was processed and reused as a recycled paver blocks, further reducing the material waste and embodied carbon. Resilience was addressed in three scales: site, user, and building level. At site level, the climate responsive design strategies, thermal efficient material selection, passive cooling, self-shading facades helps to mitigate heat stress. To address flash flooding, the building is elevated on a stilt level, while bioswales, retention systems, and controlled drainage manage excess stormwater directing to the Adayar Creek. At user level, resilience is ensured through multiple water sources, including rainwater, treated water, and borehole water, guaranteeing continuous availability. Energy security is achieved through a combination of on-site solar generation and DG backup, and we have achieved 16 hours of autonomy. During pandemic scenarios, operable windows, natural ventilation, and fan-assisted airflow enable the building to maintain acceptable indoor quality even when the HVAC system is offline. At building level, strategically placed cores, fire-rated escape routes, smoke and heat detection systems, and BMS integrated safety monitoring enhances fire resilience. In addition, segregated waste streams and dedicated treatment system ensure robust water and waste management. Together, these strategies enable the building to anticipate risks, adapt the changing conditions, and maintain functionality during both the short-term disruptions and long-term climatic challenges. While performance is important, implementation is equally important. A sustainable building that cannot be justified economically is unlikely to be built. While evaluating affordability, one reality becomes clear. The proposed building requires a higher initial investment compared to the conventional RCC office building. This increase is primarily due to the adoption of steel structural framework, advanced building management systems, high efficiency VWF cooling, on-site water treatment, and renewable energy systems. However, these investments significantly reduces the building operational expenditure throughout its life cycle. Through passive design strategies, efficient cooling systems, on-site solar generation, water conservation measures, and durable low maintenance materials, the building achieves substantial long-term economic benefits and stronger return on investment. The final aspect of our proposal is the value it creates for both users and investors. Through stakeholder survey conducted using ELM, we found that users value sustainable workplaces when they deliver measurable benefits in comfort, health, productivity, and long-term quality of life. In response, we created a workplace that is connected to its environment, responsive to the local climate, resilient, support basic needs, has associated pride, provides better health leading to better life, and finally has a blend of tradition with strength of tomorrow. All this help in eliminating the sick office syndrome. From the investor perspective, the project demonstrates strong environmental and financial performance. Through the Griha assessment framework, the building achieved exceptional performance, scoring 100% for water, materials, health and comfort, 92% for innovation, 91% for building design, and 90% for site planning, and 83% for energy. Financially, while the project involves an incremental capital investment, there is a significant reduction in operation cost, enabling a shorter payback period. Together, these outcomes demonstrate that sustainability is not merely an environmental strategy, it creates value for both the people who occupy the building and the stakeholder who invest in it.
Establishing all these contests, the final question remains: did all these strategies give the impact what we intended? Did it work? Architecturally, the building has Architecturally, the building has satisfied both climatic and ecological aspects. The building has preserved vegetation, enhanced natural ventilation, maximized daylight, and optimized solar response. When it comes to engineering and performance, integrated steel structural system, VWF system, AI-enabled building management system, advanced water treatment, and intelligent working systems made the entire building a high-performance ecosystem. When it comes to innovation, three major things played an important role: the solar veil, the bamboo shading fins, and then the steel circular construction. When it comes to health and well-being, three things were again focused: the visual comfort, passive and active strategies, and then the indoor air quality was maintained. When it comes to energy performance, the impact was significant. The final proposed case EPI was reduced to 53.73 and has a 74% reduction when compared to a base case scenario. When it comes to water performance, the impact was even bigger. We had a 40 days autonomy and a net positive by 178%. When it comes to embodied carbon, proper material selection and life cycle based decisions gave us a 59% reduction in embodied carbon. When it came to resilience, the building had caters to power outage, water outage, fire resistance, waste management, and pandemic scenarios. When it comes to affordability, even though if the initial capital investment was higher, we have achieved a 29% reduction in operational cost, 33% reduction in life cycle cost, 40% reduction in maintenance cost, 20% reduction in utility expenses. And the 25-year trajectory shows that the cumulative savings have been 52 millions. Finally, coming to value proposition, through the surveys conducted, results that 93.3% of data-driven researchers believe that a sustainable comfort premium is worth the cost. And when it comes to the investors, the entire project has a break-even of 2.8 years, and which ultimately gives a 34.5% of ROI. So, did our project work? Yes. Today, we stand here as a team who started with a question, was challenged by the site, was pushed by our experts and simulations, and then we proved that every design decision mattered, and our response was chirp. Thank you.
Thank you, team. You gave a very insightful presentation. Let's hear the jury comments and take questions from them.
Yeah. Uh, Thanks so much for the presentation. It was pretty good. The wrap up kind of really brought out everything that you had done in the project, and showed the key elements and achievements that you'd done throughout the project. So thanks for that. I think the resilience part, you kind of captured it quite well. Although the number of days of uh, resilience, like 22 days, that it's quite a high number, and optimizing those numbers, because anytime you're looking at having energy for such a long time, it requires a lot of battery storage or some other component. So optimizing that and figuring out where's the true value, that will be helpful. But appreciate you having done that. Also, on the bifacial solar panels, I think talking about the high SRI paint to show the reflectivity to increase the productivity was appreciated. So coming to the facade, I had a couple of questions. So you talked about operable facades, and if you look. It seems like in our architectural designs requirement, you put it only on one part of the southern facade, right? On the other part of the southern facade, we still see a glazed portion without any shading. So wondering why that language was not taken over, or even the fact that suddenly in the second floor there's a tilt in the floor plate, which exposes the facade to a northeast southwest, or a different orientation, which is way more difficult to control. And why these operable systems were not used in that location, because standard fixed shading devices in those is very difficult to control heat gain and glare with those and get the optimized results. And I think a little bit of clarity on variable water flow, because some of the systems that you had mentioned in D3 were about air-cooled chillers, but there was also mention about Paharpur cooling towers, and then the reuse of water, that you recycled water in that. So I think just narrative-wise, knowing what your systems are and tightening that a little bit will help you. So it might have been that you looked at 2-3 systems and there was a little bit of a issue. And also work with your whoever was your consultant on helping you with the MEP systems, because it seems like it's not very clear where the variable flow was happening, because it seemed like they were at each floor level there were no TCUs that was shown. Very technical, but just go work with your consultants, then you'll probably get a better understanding of but overall good presentation. Yeah, that's about it.
Okay, so when you started the presentation, it was on a little lower end, but at the end, it kind of you kind of activated it and ended really nicely, and it was like summed up in a very interesting manner. And though we have already reviewed the whole document, but at the end, it was nice to have all the graphics and everything put together. So congratulations for that. So I have a few questions regarding the architectural layout. So I saw that you have a long corridors towards the external facade. So I want to understand that why did you choose to have long corridors around the facade and not indoors? Because what I feel is that because you are already heavily shading the facade, then why don't you use the right kind of light if you put those spaces this side? And the other thing is, it is also increasing a lot of floor plate area, because you just have to move around throughout the facade. If it is on the other side, it could have reduced on your floor area and could have given more area to the regularly occupied spaces. So, any take on that?
When we actually started, we had different forms, and we were working with multiple forms and stuff. And in the first layer, we understood that a linear form will work better in our climatic scenario. And since we had the banyan tree, which became our protagonist, we wanted all the interior spaces to be facing to the banyan tree. So that instead of a normal office building, which will be just glazed and which will not have a proper visual connect, we wanted most of the office spaces to be connected to that green space, and it is also connected functionally as well, the courtyard. To answer the question why this shading device was provided only in the southern side, since as I said, we wanted the visual connect, so we have placed all the corridor or the circulation spaces away from the courtyard, so that the office spaces are centered to the courtyard. And so all the circulation spaces, when it comes out, it became the southern facade. And the other reason why we actually stood by that is that in our, as we know, the sun starts from east to west through south, so the entire day has a sun hour in the southern side. So if we don't want more of solar radiation into the office spaces, whereas it can come to the corridor space, which will be less occupied when compared to an office space. And but still, instead of leaving the entire corridor space open, we went for this shading device, which, as we said, caters to three things. Instead of blocking it fully to reduce the solar radiation, we gave it a pivoted mechanism so that it can be turned with respect to the solar angle, so that it will enhance this airflow, as well as it will connect to the exterior as well.
Okay. Another question is regarding the universal accessibility integration. So you have this courtyard, and how are you integrating it with the overall floor plate at the ground levels? Somehow I didn't see or realize any ramps provided on the layout. Or have you worked on that? Because I have had this in comments.
Actually, in the ground floor layout, after your guidance, we had worked on the ground floor plan, and the central lobby space has ramp access, which directly connects to the courtyard space. So once you get into the central lobby, and then it's directly connected to the courtyard, and the courtyard is also connected to the cafeteria at the first floor level, which can be accessed through stairs as well as lift, which is being provided in the cafeteria itself. And in all other spaces also, we have provided lifts, so that, meaning in the parking space as well, so that it will make the ease of access to all floors.
Can you point out where are the ramps?
Ground floor. So basically, this was the first ramp where we can access the central lobby, and then the ramp gives us access to the courtyard.
So the integration has been done. Okay, great. Okay, so I just felt in the engineering and operations that there was some system selection and operational performance and maintenance consideration which were a little missing. Maybe a little more technicalities required there. So maybe you can discuss with the industry partners and get those things also sorted. But rest, I think it was a good presentation. Yeah, another question. I mentioned this that the Solvale wall you have mentioned was missing some radiation values. So have you worked on that?
We had actually worked on radiation,
Huh.
and then since we got some errors, we have got this sun hour analysis, where it's been proven that in our scenario, we have taken the southern facade where most of the spaces gets a sun hour of more than 8.5 hours throughout the day. And then in the Solvale, it's only 1.1 hour, which is the maximum. So since the angle of sun changes throughout the day, and since we have that pattern in an alternative layer, it will change accordingly, and which creates a self-shading pocket, and thus reduces the solar heat gain.
Thank you.
I like the presentation. It's a well shaded facade. And also what I really like is that you have the bifacial solar and then using this reflective paint to enhance the efficiency of the solar panels. I really liked it. This one I wanted to understand because the surface area remains same. How basically like you are increasing the surface area here.
So actually, we have used this AAC block, sir.
And
This is the full block which we'll get into. And then these will have this tapered, which is being tapered actually. This is also a full block which is being cut in tapered way.
Yeah.
And then due to this arrangement, for example, if the sun goes this way, there'll be shading in these areas. So as you can see now also there's a shading that you can see.
Yeah.
So accordingly, the shading will increase and decrease throughout the day. So since when compared to a flat wall, as we mentioned, the sun hours is being reduced due to this staggered.
This is an interesting thing. Wait a minute. Yeah. Yeah. Okay. Yeah. The thinking is that the surface area is increasing, right? Yeah.
But it is being
Yeah. The shade. Yeah. Correct. This is an interesting. I really liked it. So I will also go and check how it works. Okay. And there are on the water that you have taken 6 liters versus 1 liter, like a conventional 6 liters reduced to 1 liter in water closets that you have selected. So that is really challenging in the sense I have not come across those kind of water
Actually,
closets.
after having a discussion with our water expert, he asked us to go with like 3 liters or 4 liters
Correct.
maximum for one person for an office building.
Yes. Yes.
So with respect to that, we also referred the like the products that is available in the market. We have mentioned the product there too. So we for the WC we have gone for vacuum WC full for the full flush it will consume 1 liter and for half flush it will take like 0.5.
Okay.
So this way the water is reduced, the usage of water is reduced.
Yes. Yes.
Ultimately, we are productively using our water. So all those calculations were also.
Yeah.
So I also wanted to appreciate the overall affordability calculation you have done, because you have actually kind of made the point that the costing is getting higher, but the operational costing can reduce it, because obviously you are putting so many elements and a lot of systems are in place. So there will be a good capex involved, and then you are actually reducing it towards your operations. So good work.
Thank you, Team Dot. Thank you, jury members. Folks, that was our last presentation in the office building division. Our esteemed jury panel has showed immense dedication for assessing these entries, and I want to thank them. Thank you for all your thoughtful assessments and comments. Let us have a round of applause, please. And I would like to congratulate all the finalists present in the room and here at the event. Again, a round of applause, please. As the jury coordinator for this division, I've had the opportunity to see these teams submit their deliverables. They have done some incredible work. Let us not forget that these teams have discovered a way to collaborate and to do integrated design during the last 7 months. I think that itself deserves a round of applause. Coming back to our jury members, thank you for your time, feedback, and guidance. And thank you to the finalists again. These jury members will meet this evening and decide the winner and the runners up for the event. Who will it be? We will also have an exhibition called the Climate Smart Innovation Exhibition, where you get to see the products from the industry that address climate change. The exhibition is now open for you all. Please proceed to the multiplex zone, which is about 5 minutes from here. And for people who are online, we are going to end this stream now, but stay tuned to our channel. At 6 p.m., watch the 10 exhibitors pitch their product in a bid to win the Climate Smart Innovation Award. Until then, have a great evening. Before the jury begins with their deliberations and before we break out for tea, we have planned a short informal feedback session with the jury. This is an opportunity for all the finalist teams to interact with the jury members, ask questions and receive feedback from their experience in the industry, as well as from their review of your work today. We encourage to use this time well, ask thoughtful questions and make the most of the jury insights. Thank you everyone.
The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so making it cool, cool, cool. We're from SDI, net so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through and through, through. The world is so hot, hot, hot. We're making it cool, cool, cool. We're from SDI, net zero through.
My north sign is